Vice President, President of Indian Association of Physics Teachers, Regional Council 08. Now I call upon Honorable Dr. R.M. Shevale sir to introduce the significance of Sub-Regional Council 08E, Vidarbha region. Please, sir.
Good afternoon, friends. Today we gathered here for the first official program organized by Indian Association of Physics Teachers Sub-Regional Council E, Vidarbha region of Maharashtra. Let me take this opportunity to say a few words about the history behind the formation of Sub-Regional Council 08E. This is an outcome of our President, Honorable Professor P.K. Aluwalia sir's vision. Since last 1 year or so, sir was in touch with few life members of IAPT from VIDRBHA region of Maharashtra, as well as with me and SRC-08 EC members, in which I can mention few names like Professor Rekha Ghorpade ma'am, our General Secretary, Dr. Abha Khandelwal ma'am, Professor Ajay Lad, Professor Shyamkant Anwane, Professor Lakhotia, Professor Mane, Principal MP Dhore from Shivaji Science College, Nagpur, etc. As everyone knows that if decentralization of the organization is done, then while conducting or organizing few activities, more people can be involved from their region and do their activities. The topic of interest in the region gets the priority. We can include such programs too. The formation of new sub-RC-08E was also discussed in EC meeting of IAPT at Jaipur Convention held last year in October 2023. The permission was pending as the proposal and the request to form new sub-RC was not in desired format. Keeping this in mind and as per our IAPT constitution demands, in last quarter of 2023, it was decided that let us come together and get at least all the details of about 100 life members of IAPT from Vidarbha region of Maharashtra. The process was started by the above members, which I mentioned earlier. The list of life members, along with an ad hoc body for IAPT SRC-08E, a request letter was sent through email to Central IAPT to give the permission for new sub-RC-08E for Vidarbha region. After a meeting of Central EC of IAPT on December 10, 2023, the proposal is approved and the permission is granted to start working with ad hoc body till December 2024. From January 2025, officially after the election, new EC for sub-RC-08E will be formed. With the ad hoc body of sub-RC-08E, Vidarbha, we are now inaugurating today's program. I now request Honorable Professor Aluwalia sir to announce the office bearers of sub-RC-08E, Vidarbha region of Maharashtra. Thank you.
Thank you very much, Professor Shevale. I'm very much pleased that sub-RC Vidarbha RC-08E has been formed. First of all, accept my congratulations to the new RC which has sub-RC which has been formed. And also I would love to thank the RC-08 Maharashtra to take this initiative to decentralize the activities of the RC-08. Now, let me just mention very briefly that there was a call which was given in one of the editorials of IAPT Bulletin that if we want to really reach out to the stakeholders, particularly students, it is very much desired that we must decentralize ourselves and a network of sub-RCs can be formed in a state. I'm very happy to note also that Maharashtra RC-08 has got the best network of sub-RCs in Indian Association of Physics Teachers. And as a result of that, what we find is that every day in one corner or the other of Maharashtra, there is a program under the banner of IAPT which goes on. And I'm also very much happy to tell all the participants here, all the honorable members here who are sitting, that we have today also launched another program, and that is to create in different institutions the student chapters of IAPT. And I believe that once this will happen, there will be more dynamism in the working of Indian Association of Physics Teachers. I congratulate the new members of this IAPT VIDRBHA Sub-Regional Council, and let me announce their names. Professor S.W. Anwane, Professor and Head Department of Physics, Shri Shivaji Science College, Nagpur, is the President. Dr. Govinda Lokhotia, Department of Physics, Bajaj College of Science, Wardha, is the Vice President. Mr. Halim Ahmad, Assistant Professor and Head Department of Physics, SFS College, Nagpur, is the Secretary. And Dr. Gajanan Jadhav, Assistant Professor, Department of Physics, Shri Shivaji Science College, Nagpur, is the Treasurer. He is also the master of the ceremony of this program. Also, there are executive committee members in it. Dr. Abha Sunil Khandelwal is the executive committee member, and she has really taken a lot of interest in the formation of this sub-RC. Let me also tell you that she is basically a computer scientist, but has a lot of interest in physics. And I'm sure that her presence in this sub-RC will add some more flavor to the activities which are on the interface of computer science and physics. Then we have Dr. Ajay Bhaura Lad. He is Professor and Head UG and PG Teaching Department of Physics, Amolak Chand Mahavidyalaya, Yavatmal. Dr. Pankaj Nagpure, Professor, Department of Physics, Shri Shivaji Science College, Amravati. Dear participants, let me tell you that Dr. Pankaj Nagpure is also a recipient of the Best Teacher Award of the Indian Association of Physics Teachers. Dr. Ashwini Kumar Vajpayee, Head of Research Center in Physics, former Head Department of Physics, Srimati Narsamma ACS College, Kiran Nagar, Amravati. Dr. Amol Nande, Assistant Professor, Department of Physics, Guru Nanak College of Science, Balarpur. Shashank Deshpande, Department of Physics, Junior College, Hislop College, Nagpur. And Dr. Prashant Ambekar, Associate Professor and Head Department of Physics, Dharampet, MP Dio Memorial Science College, Nagpur. So these are the members. And once again, let me congratulate you on this occasion. That you have started on a very, very nice note. I think you have picked up a very interesting theme to showcase physicists of India to the physics community, not only in IAPT, but beyond. Thank you very much.
Thank you so much, sir. Once again, congratulations to all the office bearers of IAPT Sub-RC-08E. Today we have with us President of IAPT Sub-RC-08E, Dr. Shyamkant Anwane, sir. Dr. Shyamkant Anwane, sir, serves as the Professor and Head of the Department of Physics, dedicating the past 25 years to the field of physics education. He has been an ambassador for Maple software for the last 5 years and is a renowned instructor on Udemy, an esteemed international online learning platform. Dr. Anwane has successfully conducted 2 online certificate courses on Udemy, attracting a global classroom of approximately 4,000 students. His commitment to academic excellence has taken him to various countries, including Singapore, Turkey, and the USA. Nominated to the Board of Studies of RTMNU Nagpur University for Applied Science and Humanities for a period of 5 years. Dr. Anwane has previously contributed to the BOS for Autonomous Bajaj Science College, Wardha. His scholarly achievements include the publication of 5 books and around 20 research papers. Dr. Anwane has completed UGC, MRP, UGC, COC, and the UGC innovative projects. Additionally, he has developed the Android mobile app Physics Pro, available on the Google Play Store and runs an educational YouTube channel. So now I call upon Honorable Professor and Head of the Department of Physics, Professor Shyamkant Anwane sir, for the introductory remark. Please, sir.
Thank you, Jadhav sir. Am I audible?
Yes, sir. Yes.
A very good afternoon to one and all present here. I remember the great Maratha warrior Chhatrapati Shivaji Maharaj and pay my tributes to the founder president of IAPT, Professor D.P. Khandelwal. Professor Khandelwal established this Teachers Association of 4 decades ago, and we are into the 40th year of its existence. And this very program of the day is an outburst of Professor Khandelwal sir's vision, I believe, and I'm honored to be part of it. I'm happy to mention that IAPT stands as a unique example in our country, like an association having such a great network. I also pay my humble homage to Dr. Punjab Rao Deshmukh, who has been the first agricultural minister of independent India and founder of my parent society, that is Sri Shivaji Education Society Amravati, and it's my governing society of this college, which is popularly known in the town as Sri Shivaji Science College, Nagpur. I recognize the presence of Professor P.K. Ahluwalia sir, National President of IAPT and a wonderful professor of physics committed to students and the subject. Professor Sri Roop Rai Chaudhary, a versatile professor of physics working with the National Institute of Repute TIFR. Professor Rajinder Modgil, professor at Kurukshetra University, a doctoral research student of Professor Ahluwalia sir. Principal of my college, Professor Mahendra Dhore, a dynamic administrator and a man of computer science. Professor Raghunath Shewade sir, President of Regional Council of Maharashtra and a wonderful teacher. My colleagues at SRC-08 and my colleagues at the Department of Physics, Sri Shivaji Science College, Nagpur, and dear student friends. Today I am speaking on behalf of entire Sub-Regional Council for VIDRBHA, known as SRC-08. I am overwhelmed with the responsibility bestowed on my team and the trust that National President of IAPT, Professor Ahluwalia sir, and Professor Shewade sir has shown upon us. On behalf of our team, we shall put our best. I would say that we shall put our best to reach to students in the best possible way. With the designation of IAPT, I experience empowerment in making such programs more effective, not only in getting eminent resource persons, but also reaching students through the network of IAPT composed of like-minded teachers and students. Looking forward with positive mind and lot of hopes, I will conclude my my words for the further proceeding. Thank you, Jadhav sir.
Thank you so much, sir. I just forgot to recognize one name over here. That is Professor Lata Jadhav ma'am, who is Secretary of IAPT. I welcome you, ma'am. Thank you so much, sir. Today we have with us as a guest of honor our beloved Honorable Principal, sir. Now I call upon to Ms. Sakshi Nalle to introduce Honorable Principal Professor Mahendra Dhore, sir.
Good afternoon, everyone. I am highly honored and privileged for this given opportunity to introduce our principal, Professor M.P. Dhore, sir. Sir has completed bachelor's, master's, and PhD degree in computer science from Amravati University. Sir has more than 27 years of teaching experience at UG and PG level. Sir has completed major and minor projects and published 46 research papers in international journals, presented 22 research papers in various national and international level. Sir has attended 58 workshops, conferences, and refresher courses. Sir has also visited Malaysia, Singapore, and Thailand on various academic assignments. Sir has handled various responsibilities and positions. Firstly, Sir has received Dr. R. Krishna Kumar Gold Medal for the Best Principal Award from Nagpur University 2023. Sir is the chairman of Board of Studies in Computer Science, member of Senate and member of Academic Council of Rashtrasan Tukaroji Maharaj Nagpur University from 2022 to 2027. Sir is also a member of Recognition Committee of Nagpur University and Gondwana University, Gadchiroli. Sir is a member of ad hoc Board of Studies in Computer Science in New Model Degree College, Hingoli, Nanded. Sir was a member of Academic Council of Rashtrasan Tukaroji Maharaj Nagpur University in Nagpur. Sir is a member of Academic Council and a member of Board of Studies in Computer Science, JB Science College, Wardha. Sir is a member of Board of Studies in Computer Application, KK Sanskrit University, Ramtek. Sir is an ex-coordinator at Nagpur University for the spoken tutorial project of IIT Bombay. Sir is a member of Board of Studies in Computer Science and member of Faculty of Science of Sant Garge Baba Amravati University in Amravati and many more. We are happy to have such a dynamic personality with us today. I now request our principal sir to say few words on this occasion. Thank you, sir.
Thank you very much. Firstly, I pay my homage to the founder of Sri Shivaji Education Society, Amravati, Dr. Panjabrao Alai Bhausaheb Deshmukh, the first Union Agriculture Minister. I take this opportunity to remember the great saint Rashtrasanta Tukaroji Maharaj, after whom our Nagpur University is renamed. Our today's guest speakers for this one-day national seminar on life and work of S.N. Bose, Dr. Srirup Rai Chaudhary sir, Professor Rajinder Mudgil sir, Professor Ahluwalia sir, prominently present on this online platform, Dr. Mrs. Khandelwal madam, Dr. Shewale sir, and organizer Dr. Professor Shyamkant Anwane from Shivaji Science College, Nagpur, and all the office bearers of this IAPT VIDRBHA chapter, and all the researchers, teachers, and students who are attending this seminar in online mode. A very good afternoon to one and all. Firstly, I must congratulate Dr. Ahluwalia sir, being the mentor of IAPT, for allowing me to be a part of this IAPT activity twice, because today is the second time I am being a part of this IAPT activity being organized at Shivaji Science College. And for this, I must thank Madam Khandelwal, who has taken keen interest in associating our college with the IAPT. Thank you, Madam. At the same time, Ahluwalia sir has extended his cooperation to the Department of Physics of this college by allowing the formation of this sub-regional council of Maharashtra, VIDRBHA SRC-08, and accordingly the formalities have been done, and today we are declaring the formation of this sub-regional council. I take this opportunity to congratulate all the office bearers of this sub-regional council of Maharashtra, including President, Vice President, Secretary, and all the executive members. Congratulations to all. At the same time, I must thank the organizers for allowing me to be part of this activity, wherein renowned scientists of the country, Dr. Srirup Rai Chaudhary and Professor Rajinder Mudgil sir from Kurukshetra University. They are the resource persons for this national seminar, and they will be delivering on the life and work of Satyendra Nath Bose and Bose-Einstein condensation, prediction and realization respectively. So I don't want to be in between the actual academic feast. Once again, I thank IAPT and all the organizers for making me a part of this activity. I wish a grand success to this national seminar. Thank you very much.
Thank you so much, sir. Today, we are celebrating the birth anniversary of Satyendra Nath Bose. Satyendra Nath Bose was an Indian mathematician and physicist specializing in theoretical physics. He is best known for his work on quantum mechanics in the early 1920s, in developing the foundation for Bose-Einstein statistics and the theory of the Bose-Einstein condensate. A fellow of the Royal Society, he was awarded India's second highest civilian award, the Padma Vibhushan, in 1954 by the government of India. So today we have with us one of the well-known physicists and the guest speaker, Professor Srirup Rai Chaudhary sir, who's going to speak on the topic of the life and work of Satyendra Nath Bose. I would like to request my colleague, Dr. Sugandha Khangar ma'am, to kindly introduce our today's guest speaker. Please, ma'am.
Giving me this opportunity to introduce such an eminent personality, Professor Srirup Rai Chaudhary sir. He is a professor of theoretical physics and dean at TIFR. He specializes in the study of elementary particles and their interactions, especially the theories of electroweak interactions and unification of forces. He studied physics at Presidency College, Kolkata, and University of Calcutta, and was a postdoc at TIFR and CERN. He taught at IIT Kanpur for some years before joining TIFR. Apart from his research and teaching work, he is interested in science popularization and in the history of science, especially in the context of development of modern Indian science. Now, I would like to request guest speaker of today's program, Professor Srirup Rai Chaudhary sir, to deliver his talk. Sir, please.
Thank you very much for that very nice introduction. Can you hear me?
Yes.
Can I be
Yes,
heard?
sir.
Yes.
Yes, sir. You're audible.
Okay, let me share my screen first, and then I'll. Is the screen visible?
Yeah, yeah.
Yes, sir.
Yes, sir, it is.
Okay, let me start. So thank you very much, Anwane sir, and all the other organizers of this for inviting me. And I also take this opportunity to thank the newly elected Executive Council of the VIDRBHA chapter of IAPT for this organizing for the responsibilities, and I hope we have a very good term. I also would like to thank the IAPT in general for organizing this program, and it is fitting that we do this on the 100 years anniversary of the famous discovery of Bose statistics by Satyendra Nath Bose. So I will be talking about his life and work. And if you look at this colorful thing which is on the screen, this is not just a decoration. It is actually a simulation of a Bose-Einstein condensate. And in the midst of it, let me show you the man himself. So that was S.N. Bose. But let us begin this story right at the beginning. So the early part of the 19th century, 20th century was described by George Gamow in his famous book as 30 years that shook physics. And here are the people who were responsible for it. They're all familiar names. They are all in our textbooks. And if you look at them carefully, you notice something, that they are all Europeans, all Caucasian in nature, all white men, with one exception. And one stands out, completely different, and is the person about whom we are going to talk. But let's begin our story. I'm sorry, I have a bad throat, so I will keep sipping my tea throughout. Please forgive me for that. So we start the story by taking you back to Europe in the middle of the 19th century and to the spot which is flashing in red over there. That is the beautiful town of Munich. So Munich with its very famous cathedral, that twin tower building. And in Munich in the 19th century, there lived an optician called Joseph von Fraunhofer. And what Fraunhofer, so he is the person standing in the middle of the picture. So Fraunhofer invented an instrument called the spectroscope, which essentially is a prism and a telescope to focus it, by which you can look at distant objects, especially stars, and find out the spectrum of the light coming from there. So the most obvious thing to look at in this is, of course, the sun. So when Fraunhofer looked at the sun, he found, of course, something very interesting. Of course, you see below a picture of the solar spectrum. These are the famous 7 colors discovered by Newton. But in the middle of them, you see that there are these black lines. And these lines are today known as Fraunhofer lines. What is even more interesting is that he discovered that when there is a solar eclipse, the same lines become bright lines. Let me repeat that. Keep your eye, for example, on these two black lines, dark black lines in the yellow. See what happens during the eclipse. They shine out as yellow lines. So nobody could understand this. So about half a century later, the understanding did come. It came with the work of these two gentlemen, Robert Bunsen, who invented the well-known Bunsen burner, which you use in your laboratory, chemistry laboratory, and his assistant and later colleague, Gustav Kirchhoff. So Bunsen and Kirchhoff, what they discovered is that if you put different elements in the Bunsen flame and you look at it through the spectroscope, you see line spectra, exactly the kind of lines which I showed you there. And they found that the frequencies of many of the Fraunhofer lines are matching with the line spectra of the elements. Now, Kirchhoff took this further and he proved using thermodynamics that this is because the absorption and emission spectra have to be the same. That is why what you are seeing, those black lines you see in the Fraunhofer spectrum, are the lines which belong to the solar atmosphere of the corona. Now, when the sun is bright, they are absorption lines, they are absorbed in the corona. But when the sun is obscured and you see only the corona, then the same lines come out as bright lines. And here is Kirchhoff's law in mathematical form. It said that the emissivity for a particular wavelength that's given a given temperature divided by the absorptivity, so the rate of emission versus the rate of absorption per unit time, is a constant. It's irrespective of what material you look at, whether it is the sun or a star or a bright object or an electric bulb or whatever, it will be the same. And therefore, this is also the same for an object called a black body, which absorbs all wavelengths. So for a black body, this absorptivity is 1, irrespective of whatever value lambda and t takes. So we might as well remove that 1 and we write just E lambda. So the finding out this function, this E absorptivity, let us say, emissivity of a black hole, black body for different temperatures is or was a big challenge to find out this function. And in fact, we know what the function looks like today. It was actually nicely measured by these two gentlemen, Otto Luhmer and Ernst Springsheim, and it has this form. As you vary wavelength, the intensity or the emissivity goes up and then it falls and then it goes to 0 as you go to very large wavelengths. And out of the wavelengths measured only, and for lower temperatures, the whole curve is reduced and it moves towards the right, that is towards larger wavelength. As it becomes hotter, it moves towards smaller wavelength. And what you see here is the range of frequencies which correspond to light. Beyond this, on this side, we have ultraviolet radiation. On this side, we have infrared radiation. And if you go further away, you will have microwaves, radio, and so on. Now, the question was how to understand this. So the first person to develop a formula for understanding this was a gentleman called Wilhelm Wien. And he was also at Munich. So what Wien developed a formula which worked well for the low wavelengths. But for high wavelengths, we are comparing the 7000 K line. And for high wavelengths, it went off and was totally wrong. And this is a big deviation. So his was the first attempt. A better attempt was made by Lord Rayleigh and Sir James Jeans. And they came up with a formula which is known as the Rayleigh-Jeans formula, which on the other hand worked very well for large wavelengths or small frequencies. But as you went to lower wavelengths, this curve just went up, and for wavelengths close to zero, it just became infinite. Now that is what you call an ultraviolet. It's called a catastrophe, because in the ultraviolet, if you integrate the total energy here, it will come to infinity. And no black body, of course, can emit an infinite amount of energy. Now, the failure of the Rayleigh-Jeans formula, it gave a big jolt to physics. Now, why is this? It is because it's almost breathtakingly simple how they arrived at this formula. So let me start by telling you that Kirchhoff, in proving his famous law, he has shown that the radiation confined inside a cavity. So let's imagine this is a cavity with reflecting walls, and a ray of whatever radiation comes in here, gets reflected inside and gets confined. So the spectrum of this is the same as the radiation emitted by a black body. So this is some beautiful proof by Kirchhoff using thermodynamics. And in fact, this had been proved by both Boltzmann, that the law discovered by Stefan, you see on the right side, that the radiation emitted by a black body per unit area is proportional to the absolute temperature to the fourth power, which is known as Stefan's law, is actually can be proved using the same concept of cavity radiation. So Boltzmann, it's now known as the Stefan-Boltzmann law. And by showing this, he had proved that yes, this idea is a good one. It's the right track. Now, Boltzmann had also used this to prove something called the equipartition theorem, which we will come to. But what the Rayleigh-Jeans formula did was it simply counted the number of degrees of freedom of this cavity radiation and gave them the same energy. So let's see what he did. So Lord Rayleigh, he just counted the number of vibration modes of a standing wave inside a cavity. This is similar to what you do with organ pipes and so on. And he obtained that the number between the frequency nu and nu plus a small change is given by 4 pi nu squared by c cubed, where c is the velocity of light of electromagnetic radiation. Very simple formula. However, Sir James Jeans suggested that there should be a factor of 2. Why is that? Because each of these modes of vibration also has 2 polarizations. Because light is a transverse wave, and therefore it has 2 degrees of polarization. So we add this factor of 2. Then they combined this with Boltzmann's law of equipartition of energy, which is that each mode will get the equal amount of energy, Boltzmann constant into T, kT. So multiply by kT. And what we have, this is the simple formula, which is known as the Rayleigh formula. Now you see a problem with this. Frequency is inversely proportional to wavelength. So this actually goes as 1 by lambda squared, where lambda is the wavelength. And what happens at low wavelengths? This thing goes to infinity. Or at large frequencies, this goes to infinity. So there is no help for this. But this seems to be the most straightforward thing you can do. You count the number of modes, multiply them by the energy of every mode, and you have got the total energy. I mean, where can that go wrong? So when you have a puzzle like this, what do? You call in a detective, but we'll come to that. So where could one have gone wrong? So let's see. First of all, the wave nature of radiation, the counting of wave modes is a simple thing. You do it in +2. And the wave nature of radiation, I'm showing you a diffraction pattern from a laser, but you can see it in small experiments. There's no question that light diffracts, so therefore it has a wave nature. Secondly, if you see the Polaroid glass, or you have Polaroid glasses, then you know polarization is an everyday phenomenon nowadays. So there is no question that light has 2 degrees of polarization either. So now if you have a puzzle like this, you call in a detective. So we call in the most famous detective of all time. And Sherlock Holmes had said that it is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. So the only one left is the equipartition theorem. The equipartition theorem has got to be wrong. But there's an issue with that. How can it go wrong? I'll show you a derivation. It's very, very simple. So let's see. The amount of energy which can go into any mode, let's say, is arbitrary. It's a quantity E. And the probability for this is given by the famous Boltzmann factor, which is exponential of minus E by KT. All right. So the average energy, very simple. Take the energy, multiply by the probability, and integrate over all energies, divide out by the total probability. Now here in this second term, I've simply substituted the form of the probability. And we have this form. And it is integral. You do these integrals. If you do them, the numerator comes out to be KT whole squared. Denominator is KT, so the ratio is KT. And this then is the average energy, which goes into each mode. So this is the famous equipartition theorem of Boltzmann. So, I mean, how could you go wrong? So it was Max Planck in 1900 who made an inspired guess. How could you do that? He asked the value question, what if the energy values, see, remember we had done an integration. Here I did an integration. Suppose it's not an integration, but a summation. What if the energy values are integral multiples of some energy packet? So let's imagine energy comes in packets. So there is some basic packet, E0, and N is a multiple of that. So, we have multiples of these packets coming together. So in that case, you would have E, instead of this formula, which I had just written in the previous slide with integrals, you would replace them by summations. So you would have a summation, and this N of N corresponding to the integer N would be N times E0 over KT. N times E0, I've just substituted for En. And this is the average value. Sum over N is from 0 to infinity because all possible sizes of packets should be considered, all possible energies. Now again, you can do this sum quite easily. And if you do it, it requires this form. So the numerator has this complicated form. The denominator has a similar form. So if you divide out this and simplify this, you get the form on the right side. A0 over e to the e by kt minus 1. So it's not the same as equipartition. So for different values of E0, you will get different values. And for different values of KT, also you will get different values. So now it's no longer a simple equipartition law. It's a more complicated equation. So let's now plug this into the Rayleigh-Jeans formula and see what happens. One thing we note is that when E is small, this E0 or N is small, then what happens is that if E0 is small, you can expand this exponential as 1 plus E by KT. So the 1 cancels and you get E by KT below. E0 cancels and you get KT, which is the result, which is the equipartition theorem, which was used by Rayleigh and Jeans. So Planck concluded that this small E0 must occur where the Rayleigh-Jeans works. And it works well for large wavelengths, that is small values of frequency. In other words, that when E0 is small, that works for small frequencies. So if that is so, then at least to a first approximation, you can take E0 proportional to D, which can be written as E0 is some constant, which constant, where this H is a constant. And of course, today this is known as Planck's law. And this is constant. Very logical. But now let's see what happens when we plug all this together. So if you take E0 as H nu, then the average energy per frequency becomes H nu by E to the H nu by KT minus 1. And hence you get a black body spectrum. Remember, this is the Rayleigh's number, this is the Jeans factor, and now you multiply by this factor. This is the new equipartition theorem. So when you might do this, this is the formula you get. 8 pi h over CQ and nu cubed by this. And this is known as Planck's distribution formula. The beauty of Planck's distribution formula is that if you take the limit, we have already seen what happens if you take the limit for low frequencies, then it will match with the Rayleigh-Jeans formula. But the beauty is that when you take it at high frequencies, it matches with the high frequencies. Exponential goes faster than the power law. So what happens is the exponential dominates in the denominator, so this thing goes to 0. So you get a peak, and then it goes to 0 on the right side, and that matches exactly with Wien's formula. So it matches both the qualitative and the quantitative features of the observed black body spectrum. Moreover, if you integrate this over all energies, then you will get over all frequencies, then you will get T to the 4, which again matches with the Boltzmann-Stefan law. So it's safe to assume that this formula is right. And in fact, experiments, these are the real data of Luber and Bringstein. Schwartz and Koppler is German for black body. And experiments I almost so closely on the theoretical curves. If a student finds a curve like this in the laboratory, I think the teacher will suspect that something has been fudged. It's a beautiful, beautiful understanding. So it shows that Planck's formula really works. Now, the energy values, therefore, we must conclude that they must be integral multiples of packets. There must be energy integral multiples of energy packets. Now, however, you can ask this question, what do we mean by energy being tied up in packets? It looks completely surprising. Why would anybody believe this theory? Well, Planck thought he had an explanation. What he said is that, think of the black body, this is a black body, again, the cavity, and you think of the packets coming out discretely from the walls of the cavity. Okay, when reflected, they come out discretely. So there are these oscillators which are, in equilibrium with the radiation. These oscillators emit energy, but once they come out, then they merge into continuous standing wave patterns, which is what Rayleigh had counted. Now, how does this happen? Gives the analogy of water coming from a tap. See, imagine water falling from a tap. You can see the individual drops. It is discrete. But then you turn on the tap full force and you see a continuous stream where all these drops are still there, but they have all merged into a continuous stream. Very nice. Alas, for Planck, his own best friend, who was Einstein, killed the idea. How did he kill it? By proposing the photoelectric theory. So in his 1905 theory of the photoelectric effect, which is what really set off quantum theory, he showed that not only is the energy emitted in packets, but it's also absorbed in packets. Now, if it's emitted in packets and it's absorbed in packets, then it had better remain in packets throughout. So this packets is not a property of the oscillators, it is a property of the radiation. And of course, we now call these packets photons, as in the picture. So, as I said, if energy is emitted in packets, it must also remain as packets. Now, Robert Millikan, the famous American experimentalist, he found this idea totally repulsive, that energy can be in packets. So he set up a very beautiful experiment, which you do study in +2. And here is a beautiful the diagram, in fact, which Millikan himself had written in his paper. He wanted to prove Einstein's photoelectric equation wrong. Now, in doing so, he found this beautiful graph, which is frequency versus the voltage, that is the kinetic energy of photons. And it's a beautiful straight line. And today, in any textbook, this experiment is given as the proof that Einstein was correct. So in trying to prove Einstein wrong, he provided the definitive proof that actually Einstein was correct. And so Einstein had the last laugh. He actually won the Nobel Prize for the photoelectric effect. As a consolation to Millikan, his work also so happy ending finally. Except for Planck, we still have the puzzle. So the puzzle became worse because in 1923, Compton discovered that these same energy packets or photons, as they had been named, can scatter off electrons, and then the electron recoils. So that means that if this kind of recoil occurs, it's like a collision between two balls, and therefore it means that the energy packets also carry momentum. So there's a momentum associated with these energy packets. Now, if a particle, something carries both energy and momentum, then it's a particle. That's the definition of a particle. So light must consist of particles, though we have argued in favor of its consisting of waves. And one can guess that the ghost of Newton, who had proposed that light consists of particles, would have been pleased to hear this. However, all the experiments with light showing up as waves like this. So there is a puzzle, and the solution for this puzzle, of course, is what we solved later with quantum mechanics. However, it remained a puzzle for a long time, so people kept trying to derive Planck's law, and there was Planck's own derivation, where he assumed oscillators at the walls, and people kept trying to refine them and somehow attribute this to a property of the walls of the emitter rather than the radiation itself. So after Planck came VIDRBHA, who used probability to derive the energy transfer. It's a more sophisticated derivation of Planck's law. We got the same result. Then came a very interesting paper in 1911 by L. Nathanson. And Nathanson actually assumed the plan, proved that the photons have to be indistinguishable. Now, this didn't get much attention at the time, but we will see that Bose used the same idea later. But it was taken up to the extent that Ehrenfest and Cammellinghones, also famous for his discovery of superconductivity, they pointed out that the Einstein's photons, they cannot be Planck's distinguishable light quarter. They have to be different. And so what Planck is saying and what Einstein is saying are not the same. And as a result of this, they showed that there seems to be some discrepancy between these two theories. And basically, they were trying to rescue Planck's idea. But of course, the point here is it was distinguishable. If they are indistinguishable, they are indistinguishable. Both the theories are also indistinguishable. Well, Einstein, as is famously known, in 1916, he was also thinking of emission and absorption of radiation, which is the mechanism of the radiation interacting with the black body. So he combines Bohr's theory, which had then come, and with Planck's oscillators, and he created the famous A and B coefficients, which anybody who studies lasers studies today. Then Pauli arrived at Planck's law using this by a different thing. He took Maxwellian electrons, so having the Maxwell distribution, but he had to assume that the A and B come with a nonlinear interaction with photons. So now this is the nonlinear term. This is the density of the radiation energy contained per unit volume. This is the density of the radiation, but this is the density of radiation after the interaction. So in a sense, this violates causality. This is what Pauli had. And he was looking at collisions with electrons. Einstein and Ehrenfest took it forward. They replaced the electrons by Bohr atoms and showed that you get the same. And all of these led to derivations of Planck's law. The problem is that they were all wrong. They were all wrong because all of these derivations assume classical statistics, and photons do not obey classical statistics. So the solution, when it came from a quite different part of the world. We must remember that all of these speculations were happening where this blue circle is. Mostly in Germany, in Holland, and in similar places. The solution came from far away. It came from Dhaka. It came from what was then British India. And that is the story we have to tell. So now I will stop this for the moment, and I will tell you about the making of S.N. Bose. So this is where S.N. Bose suddenly appeared, like a meteor, and solved this problem. So first of all, let me then take you now. I started in Munich. Let us take you to Kolkata. The Google map of Kolkata, and where this red pointer is a place in the northern part of Kolkata, and it is called the Guabagan area. So as you can see from a more detailed Google map, it's a very congested and old area. And on this road, which is called Ishwar Mill Lane, this is where on 1st January 1894 on Ishwar Mill Lane, this area. In this house, Bose was born. And you can see from the condition of the house that Bose's family are still quite affluent. They have kept the house in good condition, though if you go into that area, many of the houses are very old and dilapidated. Let me also point out that it's unlikely that 1st January was actually Bose's birthday, but in those days, people didn't keep detailed records. So when he was admitted to school, somebody wrote his age as January 1st, but that is the day we follow. So the year, I believe, is correct. Now, Bose's father, Satyendra Nath Bose, was an accountant in the East Indian Railways. He was a highly cultured man, and he had founded a small factory manufacturing chemicals. We'll see that the interest in chemicals remained with Bose through his life. And his mother, Amodini, was a housewife of those times. She kept house. She bore 7 children, of whom Satyendra was the only son. Here are the 6 his sisters. And here is how his parents looked in old age, and I particularly want to look at his father, because exactly Bose came to look exactly like this in his old age. Not surprising. Well, the young Bose was educated till age 12 in local schools. He was a bright student, especially strong. And when he came home in the evening, they would all be neatly done. So Bose really loved mathematics. And he was, this whetted his appetite for more and more complicated scientific problems. At the age of 12, he was admitted to the iconic Hindu school. This is how Hindu school used to look in those days, a beautiful neoclassical building. It was the nursery of the Bengal Renaissance. Of course, today the Hindu school is a modern building, not so beautiful, more utilitarian. Now, always good at mathematics, Bose blossomed under the tutelage of his legendary mathematics teacher, Satyendra Bose. I couldn't find a picture of Mr. Bakshi, so I've shown you a cartoon instead. But what we do know is that Mr. Bakshi once gave Bose 110 out of 100 in his geometry exam, because Bose had not, this is not the problem he has solved, this is just to remind you of the typical problems you do solve in geometry. He had not only solved all the problems, but he had solved each of them in more than one way. So Mr. Bakshi said this cannot get 100 out of 100, it is to get more. And he used to say that one day, this young boy will become like a Laplace or a Cauchy. Well, that didn't happen, but he became great in his own right. Well, after this, joined the Presidency College in 1900. And so the building here on the back, right? This is Presidency College. Hair School used to be the Calcutta University, and this is where the Hindu school stood. So, having entered, but he entered the Presidency College, as you would expect, in the mathematics department. And here, he graduated his MSc in some subject called mixed mathematics, which today we would call applied mathematics. This is his mark sheet. And I have deliberately screened the marks from you because I want you to look at them. They are fascinating, fantastic. So you can guess that with a mark sheet like this, he also came first, stood first, and won the gold medal of the Calcutta University. In 1940, while still studying for his MSc, Bose got married. His bride, he was only 20. His bride was 11, but that was common in those days. And his bride, as you see here, came from an affluent family. She was the daughter of a flourishing doctor, as you can see from the amount of jewelry she's wearing. However, in those days, it was common to take a dowry. But both refused to take any dowry. It was also common that if you had a wealthy father-in-law, he would pay for your studies abroad for a bright young man. Bose refused that also. All he said is that I have 200 friends. Please invite them to the wedding feast. So he had 200 friends come to the wedding feast. So Bose, she had home common to lose in those days, but 7 of her children studied. And she was also very gracious and uncomplaining hostess, because her husband had this habit of saying, oh, so-and-so has come to see me, he's going to stay to lunch, he's going to stay to dinner. But she was always very generous and very welcoming as a hostess. And so, as you see, Bose had a large family. This is Bose in his old age. Doesn't he look like his father? And here is Ushabati in her old age, and all sons, grandsons, maybe great-grandson, actually. So Bose was very much a family man, but this came later. Once he had passed his MSc, he found himself in the great ranks of the unemployed. So what did he do? Like most unemployed students, see, he was a married man, he was soon about to become a father. He started earning a living by doing private tuitions. So many of us have done that. I've done that myself. Among his students, he had one student who became famous, not in science, but in another field. It was the young heir of the Gauripur state, which is now in Assam. His name was Pramateshchandra Barua. And he, of course, was one of the first superstars of the Bollywood film industry. And you see him here in Devdas with Devika Rani. Now, what is important here is that because he was a prince, the remuneration for the tuition was also princely. It was 200 rupees per month. Now, if that seems funny today, I'll come back to this figure later. Please remember it, 200 rupees per month. Now, there came a lucky break. Sir Ashutosh Mukherjee, a mathematician who had turned into a jurist and became a judge, he became the second vice chancellor, Indian vice chancellor of the Calcutta University in 1906. And we must remember at that time, only Presidency College and a few other colleges had postgraduate departments. There was no purely postgraduate department in the university. You had to go abroad for that. So he started postgraduate departments in many subjects in Calcutta University, including physics and chemistry. And the physics department started in 1915, the very year Bose and his friends were graduating. Now, Sir Ashutosh persuaded two of his rich lawyer friends, Sir Ashwari Ghosh and Sir Tarak Nath Bose, you see their pictures here, to donate generously for these new departments. So, in fact, Sir Ashwari Ghosh donated 21 lakhs in that time's money, and Sir Tarak Nath Bose donated 14 lakhs. Remember, this was the time, same year, okay, just 1 year before, Ramanujam had written to Hardy, as you may have read this, saying that, I'm a poor clerk and my pay is 20 rupees per month. Let's convert it into today's money. So this is 250 crores, what Sir Ashwari Ghosh had donated. It is 170 crores what Sir Tarak Nath Bose had donated. And today it is very difficult to get this kind of money even from the government. So really generous. And Ramanujam's pay also comes to about 24,000 per month, which is still what a beginning clerk gets. But now recall that Bose was being paid for his tuitions 200 rupees per month. So that is 2.4 lakhs per month. Who would not like to do a tuition if you are paid 2.5 lakhs per month? Let's go ahead. So Ashutosh, with all this money, he built an absolutely fabulous physics department in those days. So there was D.M. Bose, there was C.V. Raman, who later went on to win the Nobel Prize. Founder of statistics in India, Meghnad Saha, S.N. Bose, S.K. Mitra, and B.B. Roy, all great scientists who made an international splash in the international world. And this is what they used to be paid. So now you can scale it up yourself. Raman was paid 1,000 rupees per month. Bose was paid 600 rupees per month. Maharashtra was in Presidency College, so he was not on this payroll. And all the lecturers were getting 125 per month, which is also reasonably generous, given that poor Ramanujam got only 20 rupees a month. So what did they teach? They taught different subjects. Raman taught waves and optics, and Bose taught relativity. Quantum theory was taught by Saha. Let me introduce you to this beautiful book, which is written about this period and about these people. It's written by my colleagues Gautam Gangopadhyay and Anirban Kuttu from Calcutta University and Rajinder Singh from Karlsruhe in Germany. They've gotten together and written this beautiful book describing this period. Now, in 1919 came the Jallianwala Bagh massacre, and it marked the end of the British Raj. Why? Because after this, people came out in their millions, coming out in the open to demand freedom, which had not really happened before. This is a picture from Gandhiji's non-cooperation movement of 1921. Now, though he was sympathetic to this national movement, Bose did not actually participate in the cooperation movement. And even Sir Ashutosh, though he, of course, wanted freedom like anybody else, but he didn't approve of what he called disorderly agitation. But 80% of the students of Calcutta University responded enthusiastically to Gandhiji's call. They boycotted their classes, they publicly made bonfires of foreign goods, all the things which were happening at that time. Now, not surprisingly, the British government was not happy. So the government of Bengal, they threatened to withdraw financial support to the university. Things never changed unless 8 conditions which Sir Ashutosh described as humiliating were met. And basically, it would give the Sarkari officials complete control over the university's internal matters. As Sir Ashutosh fought this tooth and nail, he even resigned from the university, but by 1924, he was dead. And his successors meekly gave in and allowed all these 8 conditions to be accepted. However, in 1921, while this fight was going on, where the government had threatened to withdraw the financial support, one of the jobs threatened was that of Bose. Because Bose's job sponsorship, the government money paid. So at that time, with his job sort of uncertain, he decided that he had an offer to move to the University of Dhaka as a higher position, from lecturer to reader. And you see, while the British government, one side of it, from the political side, they were clamping down on the university. On another side, a British philanthropist and educationist, Sir Philip Hartog, was creating a new university in Dhaka. So everything comes in mixed form. So the new vice chancellor, Sir Philip, he handpicked Bose and a few other bright sparks, including J.C. Ghosh, R.C. Majumdar, and others, and persuaded them to move to Dhaka. The pay was also very good. Pay started at 400 rupees per month and would go all the way to 1200 per month. Now, if you remember that if 200 rupees per month meant 2.4 lakhs, then 400 was close to 5 lakhs. That 5 lakhs is very generous. Today would be a very generous salary for a beginning lecturer or even a reader. So Bose decided to take the move. To go to Dhaka, you had to take a train somewhere, then you had to take a boat on the river Padma, then you had to take a train again, but he did all this and landed up in Dhaka. Now, life as a pioneer, because the new university was being set up, is always difficult. So here is a letter which Bose wrote to Meghnad Sir. His was a very close friend. It has been well over a month since I moved to your part of the country because Saha came from the Dhaka area. Work has not yet started. Your Dhaka college had quite a few things, but due to neglect, they are in a bad way. Perhaps I need not elaborate. On the table of the sahibs are scattered lots of nickel prisms, lenses, and eyepieces. It would require a lot of research to determine which one belongs to which apparatus, and so on. Then he says, they are thinking of having a separate science library and so on. So here, Bose taught thermodynamics and electrodynamics, and at the same time, he had to set up laboratories and buy books for the library. So his hands were full. Then 2 years later came a big jolt. Again, due to fighting with the Bengal government, the Dhaka University faced a financial crunch. Again, because there was no money, Bose's regular appointment, which had attracted him there, it was changed to a 1-year contract on a fixed salary with no promise that it would be continued after 1 year. So from having a regular job with increments and so on, it suddenly became a 1-year contract. And Bose fought this tooth and nail. He wrote, that I'm afraid I can't give any undertaking to serve till October. If the university authorities persist in their unjust decision, I shall have to seek for a job elsewhere. However, the vice chancellor wrote back sharply saying, look, you're getting a lot of money, keep quiet. We'll see what happens. But he was a fair-minded man. So in March 1924, he chaired a committee which resolved the following. So Mr. Bose to continue his work as reader till the end of the present session, which was in October, to be granted 2 years study leave as from the beginning of September 94 to basically to go to Europe and study and to receive a total advance. See, the university was having a financial crunch and still he was willing to pay this nearly 14,000 rupees. Again, let's look at the modern figures, rupees 1.6 crores. So which university pays 1.6 crores for its junior faculty? But it was while this tussle was going on that Bose wrote his famous paper on black body radiation. So now I will take you to the Durga Puja of 1923. So during Durga Puja, all Bengalis generally try to go home to their homes and it was true for Meghnad Saha also. He came home to his village near Dhaka and he naturally visited his dear friend Bose, and the two had much to discuss. So, Bose, who was, teaching black body radiation, he complained that the theory of Planck is very hard to understand and students keep asking awkward questions. So it's an encouragement to the students listening to me. Please do keep asking awkward questions. You never know where they will reach. Now, Saha, who had recently moved to Allahabad University, informed Bose about the papers of Pauli and of Einstein Ehrenfest, because they didn't have a library in Dhaka, but they did in Allahabad University. And similarly, I skipped this part. So, and Pauli, I talked to you about Pauli's work and about Einstein and Ehrenfest. So these works, it became familiar to Bose. Now, Bose decided that he would do something different. He would treat the photons purely as particles, forming a gas, less like molecules of hydrogen, oxygen, etc. do. Not worry about how they are emitted or absorbed by the walls. Just treat the wall as an impenetrable thing, just like you do for molecules. Now, the statistical behavior had been worked on by Maxwell and by Boltzmann before, and they are known as the Maxwell-Boltzmann statistics. So, an important thing here is the phase space of a gas. It's a multi-dimensional space. So, if you plot x, which is the position along one coordinate, this is for one dimension, and the momentum in that direction, you can make little boxes with a change in x and change in p. And let's call the volume of that to be delta. So what you can do is, Boltzmann has shown that the number of phase cells is proportional to the root of energy, and you divide by delta cube because that's the sort of volume, and you divide by delta cube, the size of each phase cell. And then you calculate the statistical probability of distributing these particles among these cells. For this, you take any different particles in so many phase cells. So treat the phase cells, treat each of these boxes here as one of these energies. And inside each of the energy, you have so many little subdivisions. So you take different molecules that are distinguishable by the color, and you want to distribute this set of colored balls among a set of boxes, each having a large number of compartments. So the formula for this is simple. It's given by capital N, which is the number of boxes, and number of partitions to the power of the number n, which is the number of balls, divided by factorial NE. And then you take all the energy boxes, then the total number of configurations is simply the product of all of these configurations. And when n is the total number of particles in all the boxes, of course, the total energy, total number is the sum over all these energies. And you can do that integral. And you can now find the entropy of the system by using the law of Boltzmann, which is S is equal to K log W, where W is the formula which I just wrote down. Now, the second law of thermodynamics tells us that when the gas is in equilibrium, the entropy must be maximum. So you just maximize the entropy, you'll find any. Subject to these two conditions, the total number of particles must be fixed, the total energy must be fixed. So once you do that, you get a distribution which is known as the Maxwell-Boltzmann distribution. That's the form for any. This is the one which maximizes the entropy. Now notice that in this one, delta cancels. So you can now take delta to 0 without any problems. So this is the classical statistics. For an ideal gas, if you take E as half mv squared, kinetic energy only, the velocity distribution gives you the famous Maxwell energy distribution. And that has been proved by 100 experiments. Now for photons, Bose made three crucial physics assumptions. Let me describe the first two. The first one was that instead of taking some delta which you're going to take to 0, he took the phase cell to have area H. We don't know the steps by which he arrived here. Maybe he himself didn't understand it, but this really means that delta X, delta P is H, which is nothing but Heisenberg's uncertainty relation. And this is 2 years before Heisenberg had thought of it. At this point, Heisenberg had not even thought of atomic physics. He was doing fluid mechanics. So 2 years before Heisenberg, Bose used the uncertainty principle. Of course, he did not have the insights which Heisenberg had in making it, but he did use the result. He used some argument of his own, and he was very proud of it, as you will see. The second assumption he made, that the photons are not just identical, but they're indistinguishable. Now, this can only happen if they have wave and particle duality. You cannot distinguish two waves, they just superpose. So once again, it comes here, he was ahead of de Broglie also again. Now it's the same problem of distributing particles in different boxes, But now they don't have different colors. They're all identical. So if they're identical, of course, the number of configurations is less. And this is a problem which is well known. It's been discussed in mathematics since the 2nd century BC, starting from Pingala, and then many, many famous mathematicians have discussed it. Now, Bose must have known the answer, because it is known that when he was in school, he had worked out every single problem in this difficult algebra book, which was by Todd Hunter and which had been published in 1889. So here is from Todd Hunter, page 536, says to find the combinations of anything taken so many time when there are P of one sort, Q of another, and so on, which is exactly Bose's problem. And here is the answer. It's slightly different from the earlier formula, but it's still when we take all we just repeat the same thing. We take all the boxes into consideration and the photons, the total number. Okay, you find the entropy the same way. Use Boltzmann formula. The maximize of these two conditions, the total number is not fixed because photons are emitted and absorbed all the time. The total energy is. Once you have this, this leads to a distribution. Just look at the Planck distribution. It already has the Planckian form. So only thing arose from taking the photons to be indistinguishable. That's the only assumption we made. So Bose's calculation of this was also novel and far-sighted. For photons, he combined Planck's law and Einstein's mass energy relation. So E is equal to PC is Einstein's mass energy relation. E is equal to h nu is Planck's law. Combine the two, and P is h by lambda, which is today known as de Broglie's relation. Of course, he applied it to photons, which are not a issue, but when applied to matter waves, it's called de Broglie's relation. Well, when he applied this, then he found that the number of phase cells gives you this particular formula, 4 pi V by, but so per unit volume, replace the P by h nu, you have this formula. Take it per unit volume, you will get the same number of photon states as rho Rayleigh's. This is the Rayleigh formula. And when you plug in the statistical distribution, this is your result. The average energy, therefore, is this formula. And now, if you compare it with Planck's distribution formula, you find there is a factor of 2 discrepancy. So there is a 4 here, 4 pi, there is an 8 pi here. So Bose derived almost everything, but he was short by a factor of 2. This is where he had his third insight. He said, these photons are particles, so they must be spinning around their axis like planets, either clockwise or anti-clockwise, and that gives you this factor of 2. Sorry. Now, this is the concept of intrinsic spin 1 year before Uhlenbeck and Gauss-Schmidt had proposed in 1920. So Bose used all these 3 ideas before they had actually come into quantum theory. Of course, Bose didn't realize how far-reaching these assumptions were, but he did realize that he had done an important piece of work. And so he wrote it up in a modestly titled paper called Planck's Law and the Light Quantum Hypothesis. And full of enthusiasm, he sent it to a journal. This is an example of Bose's handwriting. This is not his original manuscript. He wrote up his calculation later for Einstein, and Einstein preserved it among his own papers. So it was the end of 1920 his manuscript for publication to the Philosophical Journal, the British journal called the Philosophical Magazine. After 6 months, now this is an experience many of us have had, the journal sent back his manuscript with a curt note saying, the referee report is negative, so we can't publish your paper. They didn't return the manuscript either, which is why we don't have a copy. So it was in July 1923 when his job was at stake. Sorry, the paper had been rejected. He took a bold step. He sent his manuscript to Einstein. And he wrote this letter. And this is Bose's original letter, facsimile. He writes to Einstein, respected sir, I venture to send you the accompanying article. He says, I'm anxious to know what you think of it. Then he he finds this coefficient 8 pi nu squared by CQ. He's very proud of that. He says, I found it independent of classical electromagnetism. And then he says, I do not know sufficient to translate the paper. But after that, he says, remember that I was one of the who translated your relativity into English. So it's interesting that he both writes he doesn't know German and also that he doesn't know German. I'm really sorry for coughing. So here is a facsimile of the first page of the book by of Einstein translation. This is the first English translation of Einstein's papers on relativity. It was carried out by Saha and Bose in India, not anywhere else. And Einstein, realizing that he knew to a letter, wrote back to him in German where he addresses him as dear colleague. Here is his letter. Dear colleague, I have translated your work and communicated to Few Physics. Here is what he had communicated. This is the translation. And he was not quite sure what name to put, so he just wrote Bose. It is by Bose in Dhaka University. And then the important things he says here. It says it signifies an important step forward, and I liked it very much. You are the first to derive the factor quantum theoretically. That's the Rayleigh-Jeans factor. And it is a beautiful step forward. So he writes nice things. However, he did create a problem. So you see, so he writes also to note this derivation significant advance. The ideal guess, as I will work out elsewhere. However, he neither invited Bose to collaborate with, nor did ask Bose to visit him at Berlin. He helped to publish the paper. Not only that, he created a problem by not accepting the idea of spin, because he felt the electron is a point charge, it doesn't spin. Instead, he added polarization. Polarization of a particle doesn't have any sense until you introduce particle wave duality. And then he himself says in the previous letter, if you notice here, that this is not wholly rigorously because of the polarization factor of 2. And this polarization is something he was saying, not Bose. However, it was Einstein, so Bose kept quiet. The only person to whom he opened his mind later was C.V. Raman. So Raman says in a paper later that we understand from a personal communication by Professor Bose that he emphasized the possibility of the quantum possessing, besides energy, also an intrinsic spin or angular momentum. However, this is the only place we find a recognition of this. Anyway, Einstein's postcard did serve to smooth the path to getting visa for Europe trip. And the German visa, in fact, they waived the fee. So, and that is the kind of respect with which Einstein was held. So in September 1924, Bose set sail for Europe. In fact, he was the last of his classmates and colleagues to do so. The other people I showed you earlier, they had all gone to Europe and made their names and worked with famous people. Bose was the last of them. So on November 18th, Bose reached Paris. Now you may ask why Paris when all his correspondence had been with Einstein. The reason is that one R.L. Day from Dhaka University was already in Paris. He had been sent to work with Madame Curie at the Radium Institute, and Bose's letters were being sent to Day. He needed to pick them up. He had to stop at Paris. Not only that, there was some cheap accommodation to be had at the Indian Students Association at Rue de Samarkand, and some of Bose's old friends who were actually revolutionaries who had run away from British India, they were there. So with his friends, he decided to spend some time in Paris. He was advised that if he wanted to work in Madame Curie's lab, go and first meet the theorist, Paul Lajoie. He was Pierre Curie's student. He was also close to Madame Curie. And Lajoie had actually read Bose's paper. He was suitably impressed. He welcomed this young Indian with open arms. And from then onwards, for many years, he was a friend and mentor for Bose. So he gave him letters of introduction to both Madame Curie and to the crystallographer Maurice de Broglie, who was the elder brother of Louis de Broglie. And so Bose came to meet the great lady. You see a little video of her in person. She was very ill at this time, as you can probably see, with cancer or with radiation sickness, which she had picked up from having radioactivity. But she greeted him very warmly, said she will certainly allow you to work by Radium Institute. However, because she's why did you wait till the new year and learn some French? Because your predecessor is Dr. Day. He could not communicate with people because he didn't know the language. Now, Bose was so awestruck on meeting the great lady that he forgot to tell her that he knew French. He knew French for 10 years. He could read fluently. He didn't dare contradict her. So he reconciled himself for the time being to work with Maurice de Broglie in X-ray laboratory. And then when the time came, he started working in the radium laboratory. And then, the time kept on passing. So he learned a lot of experimental techniques. He learned theory from Lajoie and Louis de Broglie. He was enjoying himself. He also made friends easily with a young doctor, for example, Bertrand Zadokan. You see them in a gesture of friendship. And also with his younger sister, Jacqueline. And they remained his lifelong friends. They even visited him later in Calcutta. Meanwhile, Einstein had translated and published a second paper by Bose, in which now Bose considers an ideal gas with massive particles in equilibrium with radiation. So there are both photons and an ideal gas. We use the same technique. Gas molecules have a Maxwell distribution, which people already knew. The photons have a Planckian distribution. Again, no interactions needed. And this time Einstein got Bose's name right. He got the place wrong. Instead of Dhaka, he writes Romna, which is the place in Dhaka, but not the city. However, only distinguishability and indistinguishability were needed. No interactions of the form Pauli, Einstein, and others had been thinking of. Then Bose wrote to Einstein, saying, I have been granted leave by my university for 2 years. May I come and work with you? And Einstein is rather warm, or I don't know how warm it should be. But he says that yes, but he's still defending his own work. I'm not in agreement with your basic principle concerning problem interaction. However, he did invite Bose to come there. But meanwhile, while all this was going on, while Bose was sitting in Paris, Einstein himself was working on Bose's idea. In July 1924, remember at this time Bose was around in Paris. He had worked on the statistical distribution of the atoms in a monatomic ideal gas, which you could now call a massive boson gas. And this is the paper. This is the Bose-Einstein statistics as we study it. Or as we would say technically, this is a gas with a chemical potential. The photon gas doesn't have a chemical potential. Then came this famous paper in January 1925. He showed that the boson gas stays at the ground state, which is what we now know as Bose-Einstein condensation, which you will hear about in the next talk. But Bose-Einstein condensation, must remember that using Bose's statistics, the discovery was by Einstein. And that is simply because he worked on this on his own. So in all these papers, Einstein acknowledged, he scrupulously acknowledged that the method he was discovering had been discovered by Bose, but he was not going to share the glory of these discoveries with some Asiatic we had never met. So Einstein was human after all. It was Paul Dirac who later coined the expressions Bose-Einstein Fermi Dirac statistics and bosons and fermions. So these names have stayed ever since. However, Bose never bothered himself about Einstein's selfishness. For him, Einstein was the god. And so after a year, he was able to finally move to Berlin and meet his hero, who was then director of the Kaiser Wilhelm Institute for Physics, today called the Max Planck Institute. And this, of course, has now become the Institute for Radiation Chemistry. It's no longer the Institute for Physics. So a little clip of Einstein, busy at his own work. And through Einstein, now Bose came to meet all the famous scientists in Berlin, who were known as the Berlin Gang. So from Planck to Lisa Meitner to Schiller to Wigner, Fritz Haber, all the famous ones, but everything revolved around this gentleman with the mustache. Then in 1925 came quantum mechanics, the famous papers, first by Heisenberg, then by Born and Jordan, and then by Heisenberg, Born and Jordan together. It created a lot of excitement. Bose wrote to Jacqueline that everybody seems to be quite excited in Berlin, the way things have been on in physics. First, on the 28th of October, Heisenberg spoke in the colloquium. Everybody is quite bewildered. There's going to be very soon a discussion of Schrödinger's papers. Einstein seems quite excited about it. The other day, coming from the colloquium, we found him jumping in the same train compartment where we were, and forthwith he began to talk excitedly about the things we have just heard. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that he is exciting the mind of the passengers. So a little impatient. Now, Einstein suggested to Bose that they should collaborate on two problems, one of which is related to the subtle interactions between the photons themselves, which there isn't, or whether he's still on his own idea. Can you derive the A and B coefficients in the new quantum mechanics? You can. Using it's a much more advanced calculation using it, but it was not possible at the time. So these were impossible problems, and not surprisingly, Bose didn't make any headway either of them. He started doing more crystallography with Hermann Mach, and he visited Einstein and had all manner of animated discussions with him, but these two problems remained unfinished, not surprisingly. By mid-1926, he came back to India. Then Bose says that working with Einstein was not easy. He wouldn't say it, but many years later, he opened up a little. He says, a close friend says, one day he was reminiscing about his Berlin days. Einstein had given a problem to solve. Satyendra Babu told me, I thought about it for 3 days, and when I went to see him with my solution, Einstein went through it and said, well, this is not wrong, but not the way I wanted. This clue does not open up any new possibility. Please don't waste my time with such trifles. That is what the old man said. So it was clear that, the 46, Einstein was now already 46. He did not like being proved wrong any more than anyone else. And in fact, this was the last of the creative things he did. Both statistics was the last of the major contributions he made to science. After that, he went off on some off track, which nobody really. I don't know what the effect on Bose was, but he did not publish again in theoretical physics till 1939, a long 15 years. Come to the part of my talk. I'm sorry, I'm running very late, but I just talk about the Bose when he came back and he was already recognized as the sage. And I will mention only the major milestones in his life. So he came back, to a hero's welcome. He had now letters from Einstein, VIDRBHA mark. Even though he didn't have a PhD, he was appointed professor and head of the department at Dhaka University. After 1 year, he was made dean of science. The laboratories he had originally not been able to set up. In 1938, he was offered the Palith professorship, which Raman had held one time in Calcutta University, but he liked Dhaka. He didn't take it. Mengla Sahar took it instead. Here is a picture which I am very proud to show you. This is the Dhaka University office of the head of the department. You can see me on the left. In the middle is Professor Ashok Sen. And on the right side is the head of department of Dhaka University, current head. And you see here that on the board behind him, you see the name of Professor S.N. Bose, 1926 till 1945, long stint. Now, what was he doing at Dhaka University? You see, he was working on electrochemistry, radioactivity, statistics. This is radiophysics. Then he comes back again to mathematics and physics around 1939, 1940. So as you see, he was a man who worked on many, many different things. There are these works on physics also. Anyway, in 1945, he left Dhaka and came back to Calcutta University. I think the Hindu-Muslim riots and feeling of insecurity must have prompted, but he had really come to love Dhaka. He did not leave Dhaka happily. And Dhaka had also come to love him. And in fact, they still love him, because here's a picture which I took myself of how they have preserved Bose's table and chairs, and his office is preserved just as it used to be, as if they are waiting for him to come back. In 1947 came independence and the second partition of Bengal. So while his other peers were all building up institutions, Bose never went that way. He was content to remain the quintessential scientist. And he was indeed nominated as a member of the Rajya Sabha, and he did accept it. He remained a member for 5 years, but he spoke only thrice. He gave only 3 speeches there. He retired from Calcutta University at the age of 62 in 1956. And for 2 years, he was the Vice Chancellor of VIDRBHA, always a tough job. And after 2 years, he resigned it. He didn't want to be an administrator anymore. So he was elected a Fellow of the Royal Society as late as 1958. And this is only because Dirac, who had visited Kolkata in 1957, was aghast. And Dirac was the president of the Royal Society. So he went back and made him a Physicist. Then he was appointed National Professor for 5 years. And this was renewed every year, every 5 years, so long as Bose was alive. Professor of his life. Calcutta University made him an emeritus professor and gave him a lab and grants to work through the Indian Association for Cultivation of Sciences. But Bose was now 65. He continued mainly to train students in experimental techniques because he felt that that is what our country needs. Moreover, the Bongyo Vigyan Parishad had been formed with Bose as president, and he continued to advocate teaching of science to the mother tongue. And this is something which he also pioneered right from 1948. In 1967, he was appointed president of the Indian Statistical Institute, and he would remain the president till his death. So 1974 was Bose's 80th year, as well as the 50th year of his discovery of Bose statistics, just as this is the 100th year. So year-long celebrations were held in Kolkata and elsewhere. A round of seminars, symposia, felicitational programs, not online, but in person, as they used to be in those days. And Bose himself was the most enthusiastic participant. And he was very happy. He felt vindicated. He said, "Now I feel I do not need to live any longer." Look at this little clip of Bose speaking at one of those. He's very old, as you can see. He walks with a stick, but is happy to speak. Unfortunately, he had his wish. I mean, all programs, they told on his health. And 1 month after his 80th birthday, he passed away quietly at his Kolkata home. And it is not since the death of Rabindranath Tagore that there was such an outpouring of public grief in Kolkata. You see here part of the cortege being taken to the crematorium with, people absolutely milling around. And so Bose's body was consigned to the flames. But Bose statistics lives on and will live on forever. And that is what we remember. Now, just a little bit about understanding Bose. See, he was not just a physicist, but he was a complete product of the Bengal Renaissance. He was a mathematician, physicist, chemist, many things. And not only that, people described him as what Shakespeare calls the milk of human kindliness. His 1923-24 work bridges the gap between old quantum theory and quantum mechanics. In fact, again, to quote Shakespeare, he could see quantum mechanics as through a glass dark. I mean, he had the right results. He may not have been sure exactly how he got it, but some amazing intuition led him to get those results. Actually, when quantum mechanics came, he didn't like it. It came in 1926. And till 1939, he was not working in quantum mechanics. He was doing other things. However, his great work was not achieved by serendipity, which means he didn't stumble upon it, but he came by deep reflection and some absolutely amazing physical intuition, which you can, it's very difficult to understand how he got those results, but he did. So one of Bose's students in his later years wrote, "One should not expect people like him to be doing routine work. He was an aristocrat. Thereafter, the final truth," he says. Well, we should remember Bose as the founder of quantum statistics and therefore a pioneer of a great deal of modern science. It doesn't matter what he did afterwards. In fact, this is enough to put him in the ranks of the immortals. After all, we don't ask, what did Dalton do after formulating his atomic theory? What did Neil Armstrong do after visiting the moon? What did Tulsidas write after Ramcharitmanas? No, these one achievements are enough for them to be remembered forever. And so I conclude by showing you this only color picture of Bose which survives. He's playing his favorite Esraj, in which he was an absolute expert and used to give programs for his friends. And on this note, I end with his famous formula. So I end by thanking you, all who have listened patiently to me, and of course, thanks to the great scientist for the things he has given us.
Thank you so much, sir, for taking us to the life and work of great scientist S.N. Bose. Having lots of historical events, happenings, and references and such a wonderful presentation. Thank you so much.
You're welcome.
Without taking much time, now we are moving on to the next. We are having with us our next guest speaker, Professor Rajendra Modgil sir. I would like to request Ms. Anushka Palandurkar to introduce the guest with the audience.
Good afternoon, everyone. Myself, Anushka Palandurkar from BSc SEMPhil. It's my honor to introduce Dr. R.K. Mudgil. Sir did his PhD in the field of theoretical condensed matter physics in 1997 under the joint supervision of Professor P.K. Ahluwalia and Professor K.N. Pathak. He joined as lecturer in 1997 at the School of Basic and Applied Sciences, Thapar University, Patiala. Shifted in 1998 to the Department of Physics, Kurukshetra University, Kurukshetra. Sir was a postdoctoral fellow for 2 years during 2002 at University of Trieste, Italy. Sir was selected as lecturer in 2007 at Department of Physics, Kurukshetra University. He was Professor of Physics at Department of Physics since January 2013 and has been Chairman, Department of Physics, Kurukshetra University during 2015 to 18. Area of research of Sir deals with theoretical study of structural and dynamical properties of correlated quantum, many particle systems in low dimensions, including quantum wells, quantum wires, quantum dots, superlattices, first principle studies of transport phenomena in nanoscale systems, etc. Sir has, to his credit till date, 52 research papers in the reputed international journals, a good number of them in Physical Review B, published by the American Physical Society, and about 60 papers in the proceedings of national and international conferences. Sir has delivered invited talks in various national and international conferences. He has made significant contribution in popularizing basic sciences. Sir has been reviewer of a number of prestigious international research journals in the area of condensed matter physics. Sir has guided 9 students for PhD and 5 for MPhil. Currently, 1 student is working for PhD. Sir has been associated with different academic and administrative assignments of Kurukshetra University, including the member of internal quality assurance cells of Kurukshetra University, UGC license officer of Kurukshetra University, NAC steering committee, etc. He has remained a member of prestigious national academic committees, including visitor nominee on the planning board of Assam University, Silchar, MHRD nominee on the board of governors of NIT Hamirpur, on the panel of NAC Bangalore, Chancellor nominee on the Academic Council of Himachal Pradesh University, Shimla. He has a rare distinction of winning 3 gold medals consecutively in BSc, MSc and MPhil examinations of Himachal Pradesh University, Shimla. Associated with Vigyan Bharati and remained Vice President and President of the Haryana unit of Vigyan Bharati. I request you to begin with the talk, sir.
Hello, very good morning. Am I audible?
Yes, sir.
Yeah,
Yes,
can you
yes.
see my presentation?
Yes, sir.
Yes,
Yes.
sir.
Yes.
Okay. Thank you very much. At the outset, I would like to express my gratitude to the organizers of this event, particularly Professor P.K. Ahluwalia, President of IAPT, and Dr. Anwane, who is President of Regional Council of IAPT, for giving me this opportunity. Well, my job is to speak on an interesting phenomena named Bose-Einstein condensation, its prediction and realization. So Professor Roy Chaudhary made a wonderful presentation covering all all life and work of Professor S.N. Bose. So here, the outline of my talk is, I shall start by discussing how the discovery of a new statistics by Bose led to the development of quantum statistics and prediction of Bose condensation by Einstein. And we shall see here that, as Professor Rai Chaudhary has mentioned, that indistinguishability plays an important role, and it is in fact epicenter of quantum statistics. So rather, there are two types of quantum statistics I will briefly discuss about, and finally about how recently Bose-Einstein condensation has been observed experimentally. So rather, my job has been made much easier because Professor Rai Chaudhary has covered all important excitement in the work of Professor S.N. Bose. But still, I will recapitulate uh, some of the important facts related to the discovery of Bose statistics. So, you must have noticed that Bose was neither a statistician by training, nor he was trying to invent something fundamentally new. He was merely not convinced with the way that Planck's had derived the blackbody radiation spectra. Particularly, Bose noticed that on one hand, Planck had used quantum hypothesis for material oscillators, which were there in the walls of the blackbody radiation cavity. On the other hand, he had employed the laws of classical electrodynamics for treating the electromagnetic radiation. So therefore, he simply decided to redrive the Planck's radiation law in a more logical and in a more consistent way. So I will skip this slide because Professor Rai Chaudhary has already discussed about blackbody radiation spectra and its theoretical explanation by Wiens and Rayleigh genes. So, Professor S.N. Bose started off in a novel way. He did not bother about material oscillators as introduced by Max Planck. Instead, he focused on the radiation that was in equilibrium with the cavity, metallic cavity. He focused on the electromagnetic radiation, and he visualized this as a gas of non-interacting photons. So he asked two fundamental questions: that for photons inside the cavity, what are the states accessible, and how these photons are distributed among these accessible states. And without going into details, uh, I have given here the expression for the equilibrium number of photons at temperature T and at frequency nu. And from here, he calculated radiation energy density and obtained the same result as earlier Max Planck and also Einstein had obtained. So I will skip this, but I just mentioned that Bose mentioned about this coefficient of 8 pi nu q by cq in the expression for radiation energy density. And he mentioned that he has obtained it, he has calculated it independent of the laws of classical electrodynamics. And another important thing which Photon introduced, it was for the first time that he treated photons as indistinguishable particles. And Professor Rai Chaudhary has already mentioned about this factor of 2. And today we would say that Bose took care of the photon spin. And it was prior to the proposal of spin by uh, Gaudsmit and Uhlenbeck in the year 1925. And paper of Bose was rejected. So here is the letter. I will skip it. So I now start from here, basically, after covering this background stuff. So when Professor Bose communicated his paper to Albert Einstein, so Einstein immediately found, he found at a glance that this work was important, and rather Einstein was moved by the ideas of Bose. He not only translated the work into German, but added the comment which Professor Rai Chaudhary also mentioned, that in my opinion, Bohr's derivation of the Planck formula signifies an important advance. The method used also yields the quantum theory of the ideal gas, as I will work out in detail elsewhere. Okay, so this is how Einstein came into the picture. So after 1 year, Einstein generalized the work of Bose to a gas of non-interacting atoms. You see, Bose studied a gas of non-interacting photons, and Einstein generalized this work to a gas of non-interacting atoms, which were indistinguishable like photons, and they obeyed the same distribution as was proposed by Bose, with the only one difference that the number of atoms here was conserved, because in the black body radiation problem, the number of photons was not conserved. So this gave rise to
Professor
an
Rajendra,
additional factor.
can you please go in the slideshow mode, because we are not able to see your slides moving on the screen.
Sorry, just a moment.
Just go in a slideshow mode, please.
Just a moment. But I am already in.
But we are,
Just a moment. Let me share it again.
yes, please.
So I am stopped sharing. So can you see slide number 8 right now?
Yeah, we can see that, but please go in the slideshow mode. For example, if you go to view, you can not views rather. There is a slideshow also.
No, I'm using the slideshow mode only.
I don't
On
know.
my screen,
Whole of
on
your
my
screen is
screen,
visible.
on
Whole
my
of your
screen.
Also
Sorry?
go to full screen mode. Also go to full screen mode. Full screen.
No, can you see, this is, I'm just pressing the button slideshow. Can you see right now?
No, we cannot see that.
Yeah, just try changing slide.
No,
Whether it changes.
just a moment.
I think he is sharing a different window.
No,
not...
can you see slide number 9 now? 10?
No.
But it
No,
works.
we can see only
We are on 8.
eighth slide.
So, okay, I don't know why it's happening so. So,
Yeah, you're not
Now it
sharing
is
the right window.
10.
slideshow, let me go from this side.
Yes, sir.
From beginning, let me
I-
see. Can you see slide number 1 now?
No, sir, from beginning you
No.
click again. Sir, please
Which-
click from beginning once again.
Yeah, I have clicked from beginning only.
Sir, right now you have clicked, once again you do it.
We are on slide number 10, sir, right now.
So
There
no
is some issue.
problem,
I
but
don't
to go
know.
from
I
beginning.
am showing it from beginning. You see, I have pressed beginning.
Sir, once
Can you
again
see
you press. No, sir, it is not in view mode.
Yes,
Yeah.
sir, right now on
Or from current slide also. Okay, do it. Do it, sir. Click it.
Yeah.
Why is it not active?
No.
No, sir.
I don't know.
I think you need to go to the green arrow for share screen and share the actual view
Once again,
mode.
share the screen.
That is where I suspect you are sharing the wrong window.
And
Just I have stopped sharing. So I am going to the button share screen.
Yes.
So here, okay, let me now check entire screen. Earlier I had selected the window only. Let me select.
please go to the entire screen. Yes.
Let me select entire screen. So, but it is not giving any option. No. When I select entire screen, so there is no option for share. So now if I select window, so okay, just a moment, entire screen. Okay, let me check entire screen. Yes, entire screen working. Share. Now let me select the entire screen. Yes. Can you see slide number 1?
Yes, sir. Yes,
Now
sir.
it is in the right mode.
Yes, sir.
Slide 2?
Yes, sir.
Slide
Yes,
number
yes,
2,
yes, yes.
3.
Yes.
Okay, I think the problem was that I selected the window only.
Yeah.
So
Now it is
let me.
fine. Now it is fine.
Can you see slide number 8 now?
Yes, sir. Yes.
Yes.
Okay. So I was here. That Einstein got here an additional factor of mu, which came from the fact that the number of atoms is conserved. Okay, so now not only this, Einstein made a beautiful prediction, which is now known as Bose-Einstein condensation. So he argued that under normal conditions of density and temperature, atoms are spread over many single particle quantum states. So you see in this expression, this n epsilon I t gives the average number of atoms present in an energy level having energy epsilon I. Okay, so under normal conditions of density and temperature, as I have tried to illustrate here, that atoms are distributed over various single particle quantum states. He argued that you keep density fixed and begin lowering temperature. So keep density fixed and start lowering temperature T. So a stage may come when this chemical potential mu can become equal to the energy of the lowest energy level. So if that happens, so clearly this exponential term will approach unity, and the denominator will approach zero, and this average number of atoms in the quantum state epsilon naught will blow up. So if so there is, if it so happens, there is a large number of, we will say, macroscopic fraction of atoms present in the same quantum state. In today's language, we will say that all these atoms have the same wave function. So he said it's a unique state of matter because, for instance, on the in the right, you can see at temperature T equal to 0 Kelvin, all the atoms are present in the lowest energy single particle quantum state, namely epsilon naught. So the prediction was basically it's Bose condensation. So it was called as Bose-Einstein condensation. Okay, so an important manifestation of the statistics discovered by Bose. So initially, this Bose-Einstein condensation was taken lightly. So Einstein was also not very much sure about this. So therefore, before publishing this prediction, before publishing this paper, Einstein wrote to the well-known Dutch physicist Ehrenfest that from a certain temperature on, the atoms condense, and without any attractive forces. Okay, that is, they accumulate at zero velocity. Okay, the theory is pretty. What is there also some truth to it? These were the words of Einstein, which he wrote to another physicist, Ehrenfest. Initially, people thought, therefore, that Bose-Einstein condensation has nothing to do with reality, and it was just a beautiful theoretical prediction. Even Einstein speculated that maybe the system of electrons in metals, hydrogen, and helium gases may exhibit Bose-Einstein condensation at low temperature. So there was a lot of speculation about this. So the picture became clear only with the arrival of quantum mechanics in the year 1925-26, where it was found that indistinguishability is a natural product of quantum mechanics. So for next 3-4 slides, I will try to discuss about the concept of indistinguishability. So here in this figure, I have shown schematically a system of identical particles in a metal. As you can see, the smaller sphere here represent the system of electrons, whereas the spheres bigger in size, they represent a periodic array of ions. So here, if we just focus on electrons, so this system, these electrons constitute identical particles. In physics, when we say identical particles, we mean that particles which have the same set of intrinsic properties or inherent properties. So in this example, for electrons, what are the intrinsic properties? The mass of electron, same for all electrons. Charge of electrons, same for all electrons. Intrinsic spin of electrons, same for all electrons. So this is an example of system of identical particles. So if we look at this system of identical particles according to the laws of classical mechanics, wherein one can follow precisely the motion of each particle in principle. So here in Hamiltonian formulation of classical mechanics, time derivative of the position qi varies according to this equation, whereas the linear momentum pi varies according to this equation. So one can follow in principle the motion of each and every particle. Therefore, one can talk of well-defined trajectories of particles. So although the particles are identical, but if we look at these particles according to the laws of classical mechanics, one can distinguish them on the basis of their distinct and sharp trajectories. On the other hand, if I look at this system of particles according to the laws of quantum mechanics, uh, then because quantum mechanically each particle, if we make use of Schrodinger's formulation of quantum mechanics, then each particle is described by a wave packet, or in terms of Heisenberg uncertainty principle, we cannot specify simultaneously, that is at the same time, the position and corresponding component of momentum of the particle. So there is inherent uncertainty in specifying the position and linear momentum simultaneously. So therefore we cannot, like classical particle, we cannot talk of precisely defined trajectories. So therefore quantum mechanically these identical particles cannot be distinguished. They are indistinguishable. This is in very brief the concept of indistinguishability of identical particles. So if I take an example of a system containing two identical particles, so quantum mechanically the state of this system is described by time dependent Schrodinger wave equation, which has been written here. So here the numerals 1 denotes all the coordinates necessary to specify the first particle. The numeral 2 represents or denotes all the coordinates required to specify particle number 2. And H12 is the Hamiltonian. So because the particles are identical, therefore, if I interchange the two particles, then the Hamiltonian remains unchanged. So it is invariant under exchange of the two particles. So quantum mechanically, one cannot talk of precise position of the particle. One can only talk in terms of probability. So probability distribution function for the coordinates of the two particles is just, you see, modulus square of the probability amplitude, or the wave function. So the principle of indistinguishability states that here, for instance, I have tried to show for two particles. The principle of indistinguishability says that we cannot find out which particle is at which location in space. So more precisely here in this example, I would say the probability of finding first particle in the volume element dr1 taken at point r1, and second particle in the volume element dr2 taken at point you see r2, this is equal to probability of finding the second particle here and the first particle here. So this is the principle of indistinguishability, because it is so, because the wave packets of the two particles overlap in space. So we cannot distinguish the particles. So if we carry out quantum mechanical theory of this problem, so one arrives at an important physical consequence of the principle of indistinguishability, which I am stating here without proof. So the result is a result of this quantum mechanical study of a system of identical particles. The result is that if we have a system of identical particles containing containing any number, then every wave function psi that describes a physical state of a system must be either totally symmetric or totally anti-symmetric. Here, the word total mean symmetric with respect to the interchange of any two particles in the system. Because if we have a system containing n particles, then different possibilities exist. You interchange one with two or one with three. So totally mean with respect to any interchange. So here I have listed such symmetric and anti-symmetric wave functions for a system that contains two particles. So clearly you can see here that the first wave function is symmetric with respect to the interchange of the coordinates of the two particles, that is 1 and 2, whereas the second wave function is antisymmetric. So if I take the particles as independent particles, then this two particle wave function can be written as the product of two one particle wave functions. And here, so that has been done. So here the particle 1 is present in the quantum state whose quantum numbers are denoted here by alpha, and the second particle is present in the quantum state whose quantum numbers are here in the state beta. Now at this stage, I asked a question that can both particles be in the same single particle quantum state? That is, mathematically, it means putting alpha equal to beta, because I said alpha denotes one quantum state, beta denotes another quantum state. So if both the particles are in the same state, that means I set alpha equal to beta. But if I do so, you see psi a vanishes identically. It becomes 0. What does it mean? That means it is not possible. Both the particles cannot be present in the same quantum state, which is nothing but, you see the statement of Pauli exclusion principle. So Pauli exclusion principle emerges as a natural consequence of the quantum mechanical description of the system of identical particles. On the other hand, if the particles are of the type that their wave function is symmetric, in that case you see psi s remains, the symmetric wave function remains non-zero. It means that for that class of particles, there is no restriction on the number of particles which can be present in a given quantum state. So having said this, now one can ask the question that for what class of particles the wave function is symmetric and for what particles the wave function is antisymmetric. Then there was found to be a relation between spin of the particle and the symmetry character of the wave function, which Pauli showed that emerges from the, you see, by combining quantum mechanics, it emerges from relativistic quantum mechanics, basically. So there was found to be a relation between spin and symmetry. And so clearly, I discussed in the previous slide that if the wave function is symmetric, there can be any number of particles present in a single particle quantum state. On the other hand, if the wave function is antisymmetric, there is a restriction. Maximum occupancy can be 1. So occupancy can be 0 or 1. So obviously, if we have a system of particles for which wave function is symmetric, so we are going to get a different law of distribution of particles among the available states. On the other hand, if the wave function is antisymmetric, we are going to get a different distribution. Okay, so the relation was that if the particles have integral spin like s equal to 0, 1, the wave function is symmetric, and the particles away is statistics, which was discovered by Bose, and later Einstein came into picture. So it is now known as Bose-Einstein statistics, and the particles which await the statistics are called bosons. Examples are photons and helium-4, etc. Okay, and for half integral spin particles like s equal to half, 3 half, and so on, the wave function is antisymmetric. Electrons fall in this category, and they obey Fermi-Dirac statistics. So the particles obeying this statistics are called after Fermi. The name is fermions. And so one can see here that, as Professor Raichaudhuri also mentioned, that Bose laid down part of the foundation for quantum statistical mechanics even before quantum mechanics was born. So only after this result, so if one want to find that for what particles one should look for what systems one should look for Bose-Einstein condensation, they should be the one having integral spin. So here are the three laws, distribution laws, which are uh, represented, which are given by this formula: average occupancy of a single particle quantum state having energy epsilon. So if you take A as -1, so we have Bose-Einstein distribution. If you have A as +1, we have Fermi-Dirac distribution. And if you set A equal to 0, so we have Maxwell-Boltzmann statistics. So here this n epsilon, average occupancy, has been shown here as a function of single particle energy. You can clearly see that these average occupancies, these distributions are distinctly different for three different classes of distributions. And here, because as the average occupancy, you can see it should always be greater than equal to 0. So for that reason, so here this chemical potential for the case of bosons should be it should be less than all allowed values of single particle energy, because otherwise this number will become negative, which is absurd. So here you can also see that in case of bosons, as you approach this as epsilon minus mu here divided by kVt, it approaches 0. So the occupancy of this level becomes very large. Occupancy of this level becomes very large. So at this stage, one may ask the question uh, that what are the conditions under which quantum mechanical effects, that is indistinguishability, should become less significant. So that point I have tried to explain here. One can introduce here, because quantum mechanically a particle in Schrodinger wave mechanics is described by a wave packet. So thermal de Broglie wavelength, it can be taken as a measure of the extension or the size of the wave packet in real space. So lambda dv has been defined here. It's just lambda equal to h by p, and this momentum is basically comes from the thermal motion. So if you substitute that, one can call this as average thermal de Broglie wavelength. So you can see here that if temperature is very high, then this wavelength is small. So particularly if this wavelength is small as compared to the average spacing between two particles, so the wave packets will not overlap, and in that limit one can regard the particles as approximately distinguishable. So in the limit of high temperature and this large interparticle spacing, that means low density and high temperature, the results of approach approximately that means you keep d fixed and you start lowering temperature. So this lambda dv will increase, as you can see here. If lambda becomes of the order of interparticle spacing, the wave packets overlap and indistinguishability should become important. Okay, and so it is under this condition that this quantum statistics should become important. And if you further lower the temperature, you can see the extent of overlap between wave packets increases, and in this limit the effect of quantum statistics should show up in the properties of the system. And here, if you lower the temperature further, that is temperature is very low and density is small, so you can see there is perfect overlap. This is the condition where one should expect Bose-Einstein condensation to happen. Okay, so the necessary condition under which indistinguishability is not important is this, that n lambda dV cube is much, much smaller than 1. On the other hand, if this object is much greater than 1, then in that limit, one should expect the effects of quantum statistics to become important. Okay, so here let me briefly discuss about the critical condition required for the occurrence of Bose-Einstein condensation. So this I will cover quickly. It is standard stuff. If we have students of MSc physics here, they study it in MSc. So one starts by considering an ideal Bose gas. Ideal mean the atoms are non-interacting. The atoms are non-interacting. So for a given volume and for a given number of particles, one can write down this relation for pressure, PV by kVt, like this. And this expression n is just total number of particles. Just add particles present in various single particle quantum states. So in this expression, beta is reciprocal of thermal energy, that is 1 by kVt, and Z is called fugacity, which is defined in terms of the chemical potential and temperature. So clearly, this fugacity, you can see, is a function of chemical potential and temperature, and chemical potential in turn is a function of number density and the temperature. So as I said earlier, that this object Z into E minus beta epsilon, this must be greater than 1. Otherwise, the argument of this natural log means that chemical potential must be less than equal to 0. So that means Z has values between 0 and 1. Particularly, Z has value 1 when mu tends to 0. So here, the sum over single particle quantum states can be replaced by an integration, as the spectrum of single particle energy states for a bulk system is almost continuous. Okay, so here we have an expression for the density of single particle states for a system of non-interacting particles. Okay, so when I do so, because here you can see that density of states d epsilon depends upon epsilon directly here as root epsilon. So if epsilon tends to 0, these density of states tend to 0. That means when I replace this sum over epsilon y an integral over epsilon, so wrongly I am giving a weight 0 to the energy level, that is ground state energy level, epsilon equal to 0. So to avoid this problem, so what we do, we take the epsilon equal to 0 term out while replacing sum over epsilon y integral. Okay, so that has been done here, as you can see. So particularly epsilon equal to 0 term has been written here in the expression p by kVt and in the expression of n. So particularly this term in case of n is just the number of particles present in the ground state, that is epsilon equal to 0. So here one can show that the first term in this term, which comes from epsilon equal to 0, this is of the order of 1 by n and natural log of n. That means in the thermodynamic limit, this term is very small. On the other hand, let us examine this term in the expression of total number of particles. As I said, this is just n naught by v. Here, n naught denotes the number of particles present in the level epsilon equal to 0. So here you can see that this term, when Z tends to 1, Z tends to 1 means chemical potential tends to 0. In that case, this n naught by v, which is the fraction of particles present in the ground level, this becomes a significant fraction of the number of particles, total number of particles. Okay, so we can say we have a macroscopic occupancy of the level epsilon equal to 0. So this is the phenomena of Bose-Einstein condensation. So here particularly, let me examine this second expression, so which I can rewrite in terms of thermal de Broglie wavelength, and this integral is defined through function g 3 by 2z. Okay, so let us examine this. So n minus n naught is just the number of particles present in the excited state. Okay, now, as I said earlier, that this fugacity for a Bose gas lies between 0 and 1. So if I plot this function, this Bose-Einstein function, so clearly we see it's a bounded function having maximum value when Z tends to 1. Z tends to 1 means your chemical potential tends to 0. So it's a bounded function. So its maximum value being 2.612. That means for a given volume and temperature, there is a restriction on the number of particles which can be present in the excited energy levels. So this is the that restriction, Ne max. So that means that for a given volume and temperature, if you increase the number of particles in the gas beyond this number, so those additional particles should en masse occupy the ground state level. So it means the condition for the occurrence of Bose-Einstein condition is that the number of particles in the system for a given volume and temperature should be greater than this. Or we can write this condition in terms of temperature. So clearly we see that for a given volume and number, if you lower the temperature of the system below this critical temperature, we have the onset of Bose-Einstein condensation. And this critical temperature, out of this theoretical analysis, what we find is that it should depend upon the number density, NYV. So more is the number density, more is the value of critical temperature. Okay. And also it depends upon the mass of the particle. Lighter is the particle, higher is the critical temperature. So one can write this condition in terms of phase space density. Again, the same factor which I had mentioned earlier, that n lambda q dV, when it's greater than or equal to 2.612. So one should get that Bose-Einstein condensation should set in. So it is a very stringent condition. It is a very stringent condition, because that means for this condition to be satisfied, we require quite a high number density and at the same time quite a low temperature. Okay, so this was the critical condition in brief. So however, after this prediction, scientists try to observe experimentally the Bose-Einstein condensation. However, this interesting phenomena, which is a manifestation of Bose statistics, this phenomena eluded experimentalists for nearly 70 years. So the problem was that, as I said here, the condition is that we should have high number density and low temperature. So if you start with a Bose gas having a given number density, which should be high, and start lowering temperature, so particle interaction effects become very important. So these interaction effects mask the effect of quantum statistics, that is Bose statistics. Okay, so because when you, for a given density, when you lower the temperature, so the because of the influence of particle interactions, there should be a phase transition from the gaseous state to liquid state, and then from liquid state to solid state, which is the stable state. Okay, so that was the reason that eluded physicists for nearly 70 years. Rather, in this regard, Schrödinger, in a monograph on statistical thermodynamics published in the year 1948, made a remark that densities required for happening of Bose-Einstein condensation are so high and the temperature so low that the interactions are bound to mask the possible effects of generation. Okay, and there is little prospect of ever being able to separate the two kinds of effects. So therefore, the strategy was that look for Bose-Einstein condensation at low possible densities so that interaction effects are least important. But if you keep density low, that is this n low, one needs to have high lambda dV. That means one needs to have ultra low temperatures. So achieving low temperature proved to be the main hurdle in realizing Bose-Einstein condensation. However, with time, advances in cooling techniques were made, particularly two interesting uh, cooling techniques were felt, namely cooling using lasers and cooling using a method called forced evaporation. So with the development of these cooling techniques, finally in the year 1995, uh, Cornell and Wyman from University of Colorado, USA, were able to actually see Bose-Einstein condensation happening in a dilute vapor of rubidium atoms. Okay, so when I say cooling using lasers, so this statement may appear strange, particularly to students, because we often hear of lasers being used for producing heat. So how lasers can be exploited to achieve cooling? This is an interesting point. Okay, so these researchers made use of a two-step cooling strategy. In the first step, a gas of rubidium atoms, which is rubidium is a boson, a gas of rubidium atoms was trapped in a trap called magneto-optical trap. I will try to briefly explain its principle, which is created uh, by lasers and by the application of a position dependent magnetic field to rubidium atoms, and then these trapped atoms are cooled by tuning laser near a resonance frequency of atoms. What is the resonance frequency? That is the frequency corresponding to transition from one quantum state to another quantum state. So in this way, temperatures of the order of 10 raised to power minus 6 Kelvin was obtained, and a density which was obtained was of the order of 10 raised to power 11 atoms per centimeter cube. So even this temperature, which appears to be very low temperature, this temperature was not sufficient for Bose-Einstein condensation. So by using lasers, one cannot go below this temperature. I will explain why. So then the items which are cooled by using lasers, they are trapped in a magnetic trap, and then they are cooled by a technique called forced evaporation technique. As the name suggests, the items having high energy or hot atoms, they are somehow forced uh, to be evaporated from the sample. In this way, one can go to further lower temperatures, which is of the order of 10 raised to power minus 9 Kelvin, that is nano Kelvin, and Bose-Einstein condensation was recorded for the first time. So now, from physics point of view, let me give you a simple explanation that how lasers can be exploited to achieve cooling. So here I take first an example where this is a container. So I first consider an example from one dimension, that is the atoms can here either move right or move left. So these big spheres, colored spheres, they represent items. So clearly you can see they are either moving to right or some are moving to left. And then on two sides of this vessel, you mount a laser which gives you a monochromatic radiation. So the laser on the right injects in radiation quanta or photons which move to the left, whereas laser on the left injects photons. So these smaller circles shown by the same color, they inject photons which travel to the right. So to begin with, the pre-cooling stage, because temperature is not that low, so one can say that velocity distribution of atoms is approximately governed by Maxwell-Boltzmann statistics. Now, how laser can slow down, because cooling means slowing down the translational motion of the atom. So what we do here in this cooling, this Doppler effect plays the most crucial role. So what we do is, here you can see that I have shown items with different colors. That means if we have a radiation quanta or photon, moving to the right. So if we have an atom which is moving towards this photon, so this moving atom experiences a frequency which is different from the frequency of the laser because of Doppler shift. So what happens? We tune the laser at a frequency which is slightly below the resonance frequency of the atom. Okay, a resonance frequency of the atom. Okay, because if we have that is smaller than that, so laser is tuned at that frequency, so that the atoms moving in a direction opposite to the photon satisfy the condition of resonance due to Doppler shift. So what happens? So for instance, here in this example, in step 1, what happens? So you have an atom moving to the right, and you have a photon moving to the left. The frequency of the laser is so selected that this Doppler shift is such that this photon is absorbed by the atom moving to the right. And if this happens, so one can apply the laws of conservation of energy and linear momentum. So atom absorbs the photon and goes to the next higher state, and as a result, its linear momentum is lowered. So here it is important to mention that if this photon is absorbed by this, so it will result in an increase of linear momentum of this atom. But it will not be absorbed because we have selected the frequency in such a way that only right moving atom, so that Doppler shift is such that it absorbs the photon. So for left moving atom, Doppler shift will be different. So this atom cannot absorb the photon. Only therefore selected atoms, that is in a particular velocity or speed interval, they satisfy the resonance conditions thanks to the Doppler effect. So after absorption, so this is an excited state. So atom returns to the ground state and a photon is emitted. Now this photon is emitted in a random direction. So here, for instance, if the photon is emitted in the same direction in which atom was moving, so the law of conservation of linear momentum tells us that the final momentum of this atom will reduce to P minus 2E by C. So this photon that absorbs, this atom which absorbs photon loses momentum in units of the momentum of the photon. On the other hand, if this photon emission takes place in the negative x direction, in that case, from law of conservation of momentum will tell us that the P will remain unchanged. On the other hand, if photon is emitted in some other direction, so as a whole, there is some component of momentum in the x direction. As a result of that, this atom will slow down. So now when the atom slows down, that means Doppler shift for this atom will change. So it is necessary to tune laser to compensate for change in Doppler shift as atoms slow down. So in this way, one can reach a stage where the linear momentum of the atom is comparable to the linear momentum of the photon. So one cannot go beyond this stage to lower the temperature, because the recoil effects become important when the momentum of atom is comparable to the momentum of photon. So this there is a limit, therefore, the minimum temperature which one can achieve in this way. So here is a schematic of magneto-optical trap and laser cooling. So in 3 dimensions, because now we have additional degrees of freedom, so one needs 3 sets of counter propagating laser beams, as you can see here, z-axis, and you see x-axis and y-axis. We have 3 sets of counter propagating laser beams oriented along the Cartesian axis, which are and the frequency of laser is tuned just below the resonance frequency of atoms in the trap. So this I have already explained, that recoil limit sets the limit on temperature which can be achieved in this way, which is of the order of microkelvins. Now what we do, lasers are, after this stage is reached, the lasers are turned off to have a pure magnetic trap. let me explain briefly how this magnetic trap is produced. How this magnetic trap is produced. So far that I go to this slide. So what we have, again, these thick arrows represent those 6 lasers. So I have a coil here through which a current is passed in anti-clockwise sense, and I have another coil here, and current is passed in clockwise sense. So because of this 2 set of coils, a magnetic field is produced in this region. Okay, so this magnetic field has been shown by these smaller arrows, that are not thick arrows, and this is an inhomogeneous magnetic field, as and the magnetic field lines have been shown here. So clearly magnetic field is strong in this region and small here, and at the center it is very small, or nearly zero. Okay, so because we have an atom in a region where specially inhomogeneous magnetic field is present, so the atomic energy levels will split. Okay, simply Zeeman effect. So because here magnetic field is inhomogeneous, so it will be a position dependent Zeeman effect. Here such splitting has been shown for the level having angular momentum quantum number j equal to 1, and here is the level j equal to 0. Here I have tried to show that what happens if the atoms moves from the center, that is from the trap, it moves away from the trap. So what happens, as for instance, as the atom moves away in the positive z direction, what happens? The strength of magnetic field changes, and hence the magnitude of Zeeman splitting changes, and you reach a stage, for instance here, where the condition of resonance absorption is satisfied. So what happens? The atoms absorbs a radiation quanta, and as a result it is pushed back. It gets slowed down. It gets slowed down. So kind of this trap. So we have a atom tries to move in the positive z direction, but because of its absorption by photon, it you can say it experiences a restoring force, so it's pushed back towards the center. So one can say here roughly, this is in brief the principle of how magneto-optical traps are produced. So one can say here magneto-optical trap is just an effect which is a superposition of the effect produced by laser light and the quadrupole magnetic field produced by these coils. So this is in very brief about magneto-optical trap. So here such a trap confines the atoms magnetically. This is magnetic confinement of atoms, so which can be which has been shown here to be represented by a harmonic oscillator type potential. So it's harmonic confinement. So this confinement is not isotropic, rather it is an anisotropic confinement. So clearly, therefore, confinement, these frequencies are different for the 3 axes, that is omega 1, omega 2, and omega 3. So interesting thing is that one can control the strength of this confinement. So therefore, what I said, when atoms are cooled to microkelvin, so one cannot go further below, so lasers are turned off. Then we have a pure magnetic trap. So it's a pure magnetic trap. So these trap frequencies, that is omega alpha square, can be controlled by via applied magnetic field. So here is the figure which I have taken from the site of Wyman, that here this is schematic of magneto-optical trap. So here green coils produce that quadrupole static magnetic field. So then we have another set of coils which have been shown here by blue color, which produce an oscillating magnetic field. So and these red lines show the set of those 6 laser beams. So now what happens? Now I briefly discuss about that how one can go further low in temperature by using the method of forced evaporation. So what we do, the trap barrier is lowered. That is, for instance, here is a stage where you have a number of atoms in the trap, and then what we do, this magnetic confinement is reduced so that the height of trap barrier is reduced. Okay, so here is that situation where it is reduced. So what happens, just like we have in a cup of coffee, that more energetic items or molecules from the cup of coffee, they evaporate. Exactly in the same way, you see the more energetic items in the trapped atoms, they escape, they evaporate. So as a result, the remaining atoms rethermalize via elastic collisions to lower their temperature. So an important thing about this about alkali items is that, because when I say that they rethermalize, so they rethermalize via elastic collisions. So for alkali atoms, elastic scattering cross sections are high. That is the reason that Cornell and Wyman selected the alkali atoms. So in this process, as you can see, that the number of atoms is reduced in the trap. That is, number of atoms is reduced mean number density is reduced. So reduction in number density mean Bose-Einstein condensation should appear at a further low temperature. At a further, although we have reduction in temperature, we have lowering of temperature, but this is accompanied by a simultaneous lowering of the number density, which means further low temperatures are required for the occurrence of Bose-Einstein condensation. So in this way, you see the temperature was lowered by using laser cooling and by using forced evaporation technique. So once this condensation has occurred, once this condensation has taken place, how does one know that Bose-Einstein condensation has occurred? So Bose-Einstein condensation mean you have a macroscopic number of atoms in the same single particle quantum state. That means as a result of this transition, there should be a change in the distribution of atoms in the trap. So particularly when the atoms condense into the ground state of the trap, they should produce a sharp peak in the radial density profile of the atoms. Okay, so so originally Bose-Einstein condensation was detected by measuring the velocity distribution of by time of flight experiment. Let me again briefly discuss about what is this technique. So it is a destructive technique. Why it is so, you will come to understand. Because what happens, let us say condensation has taken place. So what we do, what was done experimentally by Cornell and Wyman, that magnetic fields confining atoms were suddenly turned off. Okay, so there was no magnetic trap now. So what will happen? The atoms should fly apart under the influence of residual thermal and quantum energy. A residual thermal energy, what is its source? Because temperature is not 0 Kelvin. Temperature is close to 0 Kelvin. And residual quantum energy mean because atoms are trapped. Atoms are trapped. So the energy of the ground state is not zero. It is small because of Heisenberg uncertainty principle. It is non-zero energy. So that is quantum energy. So under the influence of residual thermal and quantum energy, the atoms should fly apart. And the flying pattern was emitted. So what was done? This cloud of atoms, on this cloud, a laser light was made incident, and the frequency of this laser light was selected in such a way that it is in resonant with atoms of the cloud. So what will happen? The location in the trap where so this was laser was made incident, laser light was made incident on the cloud of atoms after 60 millisecond expansion. That is, you call the time 0 when magnetic fields are turned off, and then after 60 milliseconds have passed, a laser light was made incident, and then absorption was measured. So obviously from that location in the trap where the density is maximum, okay, that is condensate part. So there should be more absorption there as compared to the locations where which corresponds to the atoms in the excited levels. So in this way, 3 bits have been shown here, taken from the original paper. So first bit is at a temperature which is more than 170 nanokelvin, and the atoms here are not yet condensed. How do we know? Because here, if this is, you can take, say, it's a two-dimensional image. This is, you can call it as x-axis, this is y-axis, and along vertical axis is the absorption which has been plotted. So clearly you can see this distribution. This profile is isotropic. This is isotropic, that it does not depend upon x and y. It is same whether you move in x direction or y direction. On the other hand, in this plot, in this picture, which is at 170 Kelvin, the condensate has begun to form. So you can see here that absorption is maximum here. That means that at this location in the trap, there is maximum density. Maximum density means these atoms are moving, are in the same energy state, or you can say in terms of velocity, they have the same velocity. And if you lower the temperature further, you can see this peak further goes up. So this is near pure condensate. So how one can say that these peaks correspond to condensate? So because these peaks are anisotropic, so the origin of this anisotropy lies in the anisotropic magnetic trap. So on the other hand, the atoms which are present in the, which are distributed in the excited states, so if you work out density from them, that density should be isotropic. So that was an important point which was made use of by Cornell and Wyman, to say that these peaks basically describe the velocity distribution of the condensate part. Okay, so there was a lot of excitement. So let me just read it out. The statements made by Wyman and Cornell. Wyman said that it really is a new state of matter. It has completely different properties from any other kind of matter. And on the other hand, Cornell said this state could never have existed naturally anywhere in the universe. So the sample in our lab is the only chunk of this stuff in the universe, unless it is in a lab in some other solar system. And they further said that if it were not for the laws of quantum mechanics, these atoms would have no energy at all. They are as close to absolute zero as the laws of science, that is laws of quantum mechanics, will allow. So for this experimental confirmation for the existence of Bose-Einstein condensation, Cornell and Wyman shared the 2001 Nobel Prize in Physics with W. Catterley. So this I will skip. So I have tried to discuss with you that how this prediction was made and how ultimately this important manifestation of the statistics discovered by Bose and how that was finally realized. So one can ask that what is the importance of achieving Bose-Einstein condensation? So I would say it has both scientific and technological importance. When I say scientific, you see we have a wonderful platform to probe these cold atoms. So as in spectroscopy, we say that colder means more accurate. So you can create number of things where you can probe the fundamental laws of physics. And coming to technological side, with Bose-Einstein condensation in hand, it is now possible to produce a coherent beam of atoms with properties very much similar to a conventional laser. So one can call it as atomic laser, where as output we have ultimate monochromatic and bright beams. So the advent of atomic laser may help to realize atomic lithography, where one can manipulate atoms or molecule atom by atom. So one can this can play important role in nano fabrication technology. So I am towards the end. This is the last slide that I just quote here probably one line was quoted by Professor Roy Chaudhary also, that there was an international seminar organized in the year 1974 in honor of Professor S.N. Bose, because that was 50 years of this great discovery by Bose. So during that seminar, Bose was asked to speak. So here is an extract from that speech. He said, "Well, after all, if one has lived through so many years of struggle, and if at the end he finds that his work has been appreciated, he feels that he does not need to live long." So prophetic words, it seemed, for Bose passed away soon after on Feb 4, 1974. So one can make this statement that Bose was no more, but bosons were here forever. So with this, I close my talk, and so I will be happy to answer if there are any questions.
Dear student, participants, and teacher, if you are having any questions, this session is open for you for the interaction with the honorable guest.
Otherwise, my email is also there in the presentation. So I will be happy if students ask questions, because I prepared this material from the point of view of undergraduate and postgraduate students, as Professor Ahluwalia sir told me.
Hello, sir.
Yes.
Yes. You
Yes,
can.
please speak.
Yes, sir. I had questions about the precise mechanism underlying phase transmissions in both Einstein condensate.
Yeah.
So basically, while phase transmission goes, then the supercondensate fluid is converted into that Mott insulator. Superfluids conduct to Mott insulator by phase transition. So what is the exact mechanism?
No. This Bose-Einstein condensation has been clearly observed. That is unambiguously observed only in dilute vapors of alkali atoms, or dilute gas of bosons. Because if there is, for instance, you are talking of Mott insulator, you see where impurities play important role. So in those kind of transitions, you see this is not a transition driven by interparticle interactions. Rather, we want to avoid these interactions, because this is a transition which is driven by uh, quantum mechanical degeneration. So interactions are not playing any role. Of course, I have discussed theoretically the occurrence of this transition in non-interacting Bose gas. Actually, even if the Bose gas is dilute, there will be some interactions. So interactions, as I have said, they intend to mask the effect of this quantum degeneration. So, for instance, if you take another related system, you talk of helium, which is another interesting system. So, helium-4 is a boson, but you see, when you cool down this helium, there is a transition from gaseous state to liquid state, and in that state, interactions play a very important role. So, one cannot unambiguously observe Bose-Einstein condensation there, but at the macroscopic level, there is superfluidity, which is a manifestation of Bose-Einstein condensation. I hope
Thank you so much, sir.
Anyone else?
There is one question in the chat box. I am reading that. My query is, what is the difference between Bose condensate and superconducting state?
Yeah. That is another important thing. That is the scientific importance of Bose-Einstein condensation. In superconductivity, when you cool the metal below a transition temperature, because they're the particles which are playing the role. These are the electrons, and thermal excitations of the ions. Okay, so this superconductivity is closely related to Bose-Einstein condensation, because as Bardeen, Cooper, and Schrieffer said, that if you cool the metal, so what happens below a critical temperatures, the electrons are paired in momentum space via lattice vibrations, that is phonons. So they form bound pair of, you have bound pairs, and in each pair you have two electrons. So this bound pair of electrons behaves like a boson. So this transition to superconducting state is closely related to condensation of those Cooper pairs.
Okay. Any other question, please?
Okay.
Well, my email is there in the presentation. If students have questions, they can also write to me.
Okay, sir. Okay. Thank you so much, sir, for having such a wonderful and excellent talk on the topic of Bose-Einstein condensation and prediction and realization. Being a host, I'm so happy. In fact, we all are so much happy and feeling blessed for having such a wonderful personalities who do not teach physics, but in fact, they live the physics. Thank you so much. Before I move on, there is one announcement that for the students and participants. At the end of the program, a feedback form link will be provided in the chat box, from which you will get a certificate of participation, and a quiz link will also be provided for which for the participants will get a separate certificate for it. So please take a note of it. Thank you, sir. Due to short of time and with the permission of Honorable President of IAPT, Professor P.K. Ahluwalia, sir, will be having Ahluwalia sir's talk later on. However, I would like to request Honorable Professor P.K. Ahluwalia, sir, to kindly sum up the today's speech, sir.
Rajendraji, please, can you stop sharing the screen?
Yes, sorry.
Please.
Just a moment.
So I think we are at the end of a very interesting session. Though we had planned 3 talks, unfortunately, there is a overlap of the Zoom meeting with another Zoom meeting. So we have to cut down. And I think it is my very pleasant duty to say to both the honorable speakers, Professor Siroop and Professor Satyendra Nath Bose, that we have thoroughly enjoyed your presentations. And the level at which you really place these topics was the one we were actually looking forward to. When I was talking to Professor Anwane, that how we should really go ahead with this program, we were actually thinking that we should celebrate Satyendra Nath Bose. It is, in a way, the 50th year after he actually left us, and the 100th year after the enunciation of the quantum statistics of bosons by Satyendra Nath Bose. So it was to celebrate that also. And naturally, Einstein is one of the figures which we cannot really forget. So the third talk we will actually have later on Monday, that is on 29th. And the time will be actually shared later. I think the kind of historical perspective and the background which was given by Professor Siroop, right from the very beginning, that when people were studying spectra, what they were finding, how it led to those catastrophes, and how it led Planck to think about all these things, and then the Einstein comes on the scene, and then the Bose comes on the scene. There was one thought which we were sharing together with Professor P.C. Deshmukh, that why we should not really think of calling this Planck's constant as not just Planck's constant, but Bose-Einstein-Planck constant. And we should actually make a kind of a submission from India to the Heritage Committee, about which I would request Professor Deshmukh to briefly tell us later. I think we should really talk about that also, because we cannot really think of whole of this scenario without dedicating Planck's constant to Professor Bose also. That was one point which I wanted to make. Then I think the kind of historical perspective which was built by Professor Seerup was just excellent. Sir, your presentation was so beautifully planned that I have no word to tell you that how good it was. And I think we will share this set of presentations on the YouTube of the IAPT also. And I must express my sincere thanks to you.
Thank you, sir.
Scale built up on top of that. And it was a very difficult actually call that please come on and give a lecture on Bose-Einstein condensate. First, even at the level of post-graduation, people do not really look at this particular topic. They read the title. After that, even teachers skip it. And Professor Modgill has shown how good a teacher he is in going through the whole process systematically, reaching right up to the experiments which actually confirm Bose-Einstein condensate's presence, and the kinds of technologies which were involved. I think it was the build-up of those technologies which took almost 70 years to reach that kind of a stage where one could detect Bose-Einstein condensate itself. So, Professor Rajendra, it was just excellent. And I think we have now two very good benefactors for IAPT also. And sir, Professor Seerup and Professor Modgill, we will keep on bothering you in future also for such excellent talks.
Most welcome.
On behalf of IAPT and on my personal behalf, I express my sincere thanks to you for accepting our invitation at a very, very short notice. And I think, Professor Seerup, we have opened a window with now TIFR for holding these kinds of seminars, which will be our pleasure. And as, sir, you know, we are a body of about 10,000 teachers from schools, colleges, and teachers. It is our duty, bounden duty rather, I would say, to reach out to our stakeholders in the best possible manner. And these are the best practices which we are trying to engage. And for that, I must thank the principal of college, Professor More, and Professor Anwane, and Professor Jadhav, who was the master of this particular seminar, to really bring together everything in a very, very systematic fashion. And I think it was a flawless seminar. Now, I would request Professor Deshmukh to please enlighten us very briefly. We have about 5-7 minutes only when we will end this seminar. So please, I request you come and please tell us what is that idea which you are actually having in mind about calling Planck's constant as Bose-Einstein-Planck's constant.
Thank you very much, Professor Ahluwalia. This has been a wonderful session. And I enjoyed both the talks very much. Professor Modgill, excellent talk. And Professor Shrirup Roy Chaudhary laid a very rigorous foundation for an appeal that I have been wanting to make through the IAPT for a long time. I have a recent book published by the Cambridge University Press on quantum mechanics, and I made a brief reference to this, that what we call as the Planck's constant should actually be called as Planck-Einstein-Bose constant rather than as Planck's constant. It is very well known that Planck himself struggled with his idea. He was not quite convinced about the foundational and fundamental aspect of a quantum of energy. He used it for curve fitting. And then the explanation really came from Einstein in 1905. I read somewhere that Planck accepted his own hypothesis in 1908. But the complete meaning of E equal to h nu gets established only after the Bose-Einstein statistics. And that is a story which Professor Srirup presented in such a brilliant manner today. So thank you very much, Professor Srirup, for such a beautiful exposition.
Thank you.
And I have two requests at this point. First is that the Indian Association of Physics Teachers and perhaps the entire Indian community in various, whatever means we have, we make a formal request to the International Union of Pure and Applied Physics, which names various symbols and standard constants and so on are authenticated by them, that H should hereafter be called as the Planck-Einstein-Bose constant. In my book, I refer to it as the PEB constant. And I urge that such a formal request is made by the Indian community to the IUPAP. The second was not so much at the top of my mind, but considering a little bit of urgency, because the American Physical Society has asked for nominations for historical sites across the world to be named as physics heritage sites. The last date for this nomination is 31st of January, which is just a few days from now. And I think that the Indian Association of Physics Teachers should nominate the Calcutta University and the Dhaka University as physics heritage sites, because the kind of physics which has come out of Calcutta and Dhaka is amazing, including the works of not just Bose, but also C.V. Raman. So there are many reasons why this should be done. And I would like to put across these two suggestions before the community this evening. Thank you very much.
So thank you very much, Professor Deshmukh. I think we will try to take up this further in whatever way we can. We can send a communication to IUPAP also regarding the suggestion for renaming the Planck constant, and also for going ahead with the suggestion of declaring Calcutta University Physics Department and Dhaka University Physics Department as physics heritage sites. Thank you very much. I also must thank Professor Shevale, who is basically the president of RC-08, and the RC-08E, which has been in a way inaugurated today, falls under his umbrella for encouraging them to come out with such a wonderful program. In fact, RC-08 is known for its innovative programs. And because we have also, Professor Srirup, a RC, sub-RC in Mumbai also, and they are very active, sir. I don't know whether you are a member of IAPT or not. I would like you to also become a member of IUPT. We would love to really have you as our honorable member.
Sure, sure.
Mr. Rajinder, we are looking forward to that. He will convert Haryana also as an independent regional council of the IAPT. He is working for that. Hopefully, in another.
Yes, sir. I will initiate, sir.
We will see Haryana RC also becoming a good hub of activities. So thank you, Professor Anwane and your team. So back to Dr. Gajanan Jadhav ji. Thank you, Gajanan ji, for hosting this.
I would like to inform the participants that we have just now provided the links in the chat box for getting your certificate and for participating into the quiz. So all participants can explore that, and I have recorded the video of today's activity and we'll make it available on YouTube through appropriate channel. Over to Jadhav sir.
Jadhav sir, please unmute yourself.
Thank you so much, sir. Thank you so much, Honorable Professor Ahluwalia sir, Honorable PC Deshmukh sir, for having your support and guidance and blessings. We are almost to the end of this particular seminar. I would like to request, call upon Dr. Halim Ahmed sir for vote of thanks.
Thank you, Jadhav sir. A very
Yes,
good
yes,
evening to one
yes,
and all.
Yes, sir, yes. You're audible.
Okay. A very good evening to one and all. I stand before you with a heart full of gratitude and immense joy as we conclude this enlightening webinar on the life and works of eminent physicist Satyendra Nath Bose. This event has been a true celebration of the knowledge and collaboration. And I would like to extend my sincere thanks to all the individuals and organizations who have made this webinar a resounding success. First and foremost, I express my heartfelt gratitude to the Honorable President of IAPT and Professor P.K. Ahluwalia ji for gracing us with his presence and formally announcing the names of the members as a ritual of the formal installation of the Sub-Regional Council of SRC-08. Sir, your support and guidance have been a guiding force in shaping the framework of this event. A special note of appreciation goes to the General Secretary of IAPT, Dr. Rekha Ghorpade, Madam, for your unwavering encouragement and support. I extend my thanks to the Professor Raghunath Shewade, President of RC Maharashtra, for your kind cooperation and invaluable assistance in organizing various programs. Your commitment has significantly contributed to the success of our endeavors. Our deepest appreciation goes to the speaker, Professor Sri Roop Rai Chaudhary sir, from TIFR, for delivering an excellent lecture on the life and works of SN Bose. Your insight and expertise have provided us with a comprehensive understanding of the legacy left behind by these remarkable physicists. I also want to express gratitude to Professor Rajendra Mudgil sir from Kurukshetra University for delivering a wonderful lecture on the Bose-Einstein condensation, prediction and realization. These lectures have enriched our understanding of these eminent physicists and their contributions to the world of science. A special acknowledgement is due to Dr. Renganayaki and Dr. Uttara Thurairajan from Regional Council, Tamil Nadu and Pondicherry for their efforts in designing an online quiz on the topics covered during this online webinar. The link of the same will be circulated just soon after this program. I extend my thanks to the principal of the Shivaji Science College, Dr. Mahendra Dhore sir, for graciously providing the platform for this event. The cooperation and support received have been crucial in the smooth execution of this webinar. I would also like to thank to our principal, Dr. Sanjay Sarve, SFS College, supporting all IAPT activities in SFS College. Last but not least, a heartfelt thank to all the organizing team members, especially Dr. Jadhav, comparing this program, and team members behind the scene who have been working tirelessly for the success of this program. Your dedication and hard work have not gone unnoticed, and it is because of your collective efforts that we can celebrate the success of this enlightening webinar. In closing, I express my gratitude to everyone who have participated, attended, and contributed to the success of this webinar. Your enthusiasm for the knowledge and collaboration have made this event truly memorable. Thank you, and we would like to, we look forward to your future endeavors together. Thank you, and have a wonderful evening. Thank you.
Yes, sir. Sri Roop sir
Thank you.
wants to say something.
No, no, I just want to say goodbye.
Okay.
Thank you.
Okay, sir. Thank you.
Thank you very
Thank you everyone for their help. And it was a delightful interaction to be here on this platform of IAPT. Thank you, Ahluwalia sir. Thank you, Modgil sir. Thank you, Sri Roop sir. Rekha madam, Shewale sir. Thank you very much.
Thank you. Thank you very much.
Thank you so much, man, everyone. Thank you so much.
Thank you, sir.
Bye bye.